something is watching us. Not a god, not a creature, not a being that conforms to anything we have ever known. It is something far larger, far older, far more incomprehensible than our tiny minds can grasp. We stand on a minuscule speck of dust, orbiting a mediocre star in the infinite darkness, spinning endlessly, imperceptibly, while asking a question so ancient and profound that even the stars seem to whisper it back to us. What is the purpose of the universe? Every atom in your body carries the echoes of cosmic history. Hydrogen crushed into helium in a star's core, carbon forged in the fiery hearts of dying suns, iron scattered across the void in supernova explosions. You are not merely in the universe, you are the universe, examining itself, pondering its own existence, and tracing its origins in your very cells. When we ask about the purpose of the universe, we embark on a journey that spans millennia, touching the minds of philosophers, scientists, and thinkers who have wrestled with this question since the dawn of human consciousness. It is a question that reaches into the deepest layers of existence, probing the nature of reality itself and our place within the cosmic tapestry. In the language of science, the universe has no inherent purpose or predetermined goal. It exists, governed by immutable laws of physics, unfolding through a chain of events dictated by gravity, nuclear forces, and other fundamental interactions. Galaxies swirl into form, stars ignite and fade, planets take shape, all as consequences of these natural processes, without intent, without design. Yet humans are creatures who seek meaning. Our minds cannot help but search for reason, projecting purpose onto the cosmos itself. We wonder if some grand design guides the unfolding of everything we observe, whether a hidden hand shapes the vast celestial dance. This urge for meaning is woven into the fabric of human consciousness and has given rise to a multitude of philosophical and religious frameworks over countless generations. Each interpretation reflects the human desire to locate ourselves in the immensity of the cosmos, to find significance amidst the silence. The question of purpose in the universe ultimately becomes a matter of personal belief and perspective. Science can reveal the mechanisms, the laws, the intricate dance of matter and energy, but it cannot provide definitive answers about why the universe exists. That realm belongs to philosophy, contemplation, and the individual mind. Our curiosity, our insatiable desire to understand our place among the stars, becomes itself a form of purpose, transforming the void into a grand laboratory of discovery and reflection. Human creations are purposeful by design. Every tool, every work of art, every structure exists to fulfill a goal conceived in the mind of its maker. We build, we create, we strive to improve, and each act is imbued with intention. The cosmos, in contrast, is an indifferent expanse. Stars are born and die, planets coalesce and drift, galaxies collide, all as a consequence of physical laws operating across incomprehensible scales of time and space. There is no plan, yet there is awe. There is no intent, yet there is infinite complexity and beauty. From the simple rules of physics emerge structures so intricate and magnificent that they inspire wonder, contemplation, and even the sense of purpose we so desperately seek. Our drive to explore the universe, to decode its mysteries, becomes a purpose in itself. The vast, seemingly indifferent cosmos transforms into a canvas for human inquiry, where curiosity is both the guide and the reward. Through telescopes and particle accelerators, through equations and observations, we trace the unfolding of the universe, finding patterns, understanding forces, and glimpsing the extraordinary complexity behind what seems chaotic. Purpose, then, may not reside in the cosmos itself, but in our response to it, in our pursuit of knowledge, in our capacity to question, to reflect, and to marvel. From the earliest civilizations, humanity has wrestled with cosmic purpose. Ancient peoples imagined gods in the heavens, divine beings who controlled the stars and planets, who shaped destinies and cast judgment. Celestial phenomena were imbued with supernatural significance, creating myths and rituals that anchored society to the rhythms of the sky. Then came the revolution of science. Copernicus, Galileo, and countless others dismantled the geocentric model, revealing a universe far vaster than our planet, far older than our species. The stars no longer bowed to humanity's centrality. They simply existed, their movements dictated by laws we could begin to understand. The 20th century expanded this understanding even further. Einstein revealed that space and time were intertwined, bending and stretching under gravity's influence. Quantum mechanics unveiled a subatomic world governed by probabilities, uncertainty, and strange interconnectedness. The Big Bang theory suggested a beginning, a singular moment from which everything emerged, a cosmos in constant expansion. Yet, even as we uncovered the mechanics of existence, the question of purpose persisted. Science could describe the how, but the why remained elusive. Some scientists maintain that the universe simply exists, evolving according to immutable laws without meaning or intent. Others ponder the anthropic principle, noting how the universe's conditions seem finely tuned for life, allowing consciousness to emerge and reflect on the cosmos itself. Philosophers and theologians suggest that perhaps purpose exists beyond our comprehension, hidden in patterns we are not yet capable of discerning. These possibilities remain speculative, dancing on the edge of evidence and imagination. Across centuries, humanity's perspective on cosmic purpose has shifted dramatically. Once the heavens were theaters of divine will, now they are laboratories of natural law. Yet our curiosity persists, our questions endure, and the universe continues to inspire. Chaos, order, birth, death, collapse, expansion. These are not acts of intent, but they form a rhythm, a grandeur, a narrative that we observe and interpret. The universe may have no purpose in itself, but through our eyes, through our questioning, through our striving to understand, it acquires a meaning of our own making, vast as the cosmos and as intimate as the atoms in our bodies. In the end, the universe watches and waits, indifferent and eternal, while we probe, we imagine, we seek. And in that act of seeking, in the dance of thought and observation, purpose emerges, not written in the stars, but in the minds that gaze upon them. However, other scientists draw attention to the striking apparent fine-tuning of the universe's constants, noting how subtle variations could have rendered the cosmos sterile and lifeless. They point to the emergence of complex structures, galaxies, stars, planets, and ultimately life itself, as potential indicators of some form of cosmic purpose, a universe seemingly tailored to foster conscious observers. This perspective, often linked with the anthropic principle, suggests that the very laws of physics, the strength of fundamental forces, and the precise mass of elementary particles appear calibrated in ways that permit the development of intelligent life. A contrasting viewpoint proposes that purpose may not be an inherent property of the cosmos, but rather a phenomenon emerging from the complexity of the systems within it. According to this idea, while the universe itself might lack an explicit intention, the rise of conscious beings imbues existence with meaning and direction, turning the universe into a canvas upon which significance is painted over billions of years of evolution. Throughout human history, civilizations have wrestled with the notion of cosmic purpose, producing a rich mosaic of interpretations reflecting their unique cultural, philosophical, and spiritual frameworks. In ancient Egypt, the universe was perceived as a meticulously ordered domain maintained by divine forces, with humanity entrusted to uphold cosmic balance through ritual, moral conduct, and devotion. Eastern philosophies such as Buddhism and Taoism, in contrast, emphasize the interconnectedness of all things, seeing the cosmos as a fluid, self-regulating system without a singular predetermined goal. Here, the focus shifts to personal harmony, enlightenment, and attunement with natural rhythms rather than adherence to a cosmic plan. In Western monotheistic traditions, Judaism, Christianity, and Islam, the universe is framed as the deliberate creation of a supreme being, with purpose intertwined with the fulfillment of divine will, moral law, and ultimate eschatological ends such as judgment, salvation, or the perfection of creation. Scientific perspectives, which have risen to prominence over the past few centuries, approach these questions with different tools and assumptions. Many scientists argue that the universe operates according to immutable natural laws, without an intrinsic purpose. Others, however, observe that the increasing complexity, self-organization, and emergence of consciousness within the universe might suggest a subtle form of purpose arising from the fundamental properties of reality. This pursuit of cosmic purpose appears intimately tied to humanity's unique capacity for abstract thought, pattern recognition, and self-reflection. As far as we can tell, humans are singular in their drive to probe existence itself, questioning not only how life came to be, but why the cosmos has unfolded as it has. This cognitive capacity allows us to contemplate phenomena far beyond immediate survival. Our brains evolve to decode patterns, predict outcomes, and construct models of reality. Yet these very faculties also propel us to grapple with concepts such as infinity, time, consciousness, and the ultimate fate of the universe. Scientific inquiry intersects with this philosophical quest, as each new discovery, from the formation of stars to the detection of exoplanets, forces us to confront questions about life's origins, the distribution of intelligence, and the underlying structure of reality. While it remains uncertain whether other intelligent species ponder their existence, humanity's search for cosmic meaning is undeniably shaped by our singular capacity for reflection, imagination, and abstraction. The vastness of the universe dramatically shapes our perception of purpose and significance. Gazing at the night sky, we glimpse only a fraction of countless galaxies, each containing billions of stars, suggesting an almost infinite array of possible worlds. This immensity simultaneously humbles and inspires, challenging anthropocentric perspectives and highlighting the precious fragility of life on Earth. The enormous distances between celestial bodies underscore the isolation of our planet, while the universe's age, estimated at nearly 14 billion years, dwarfs the brevity of human existence. These temporal and spatial scales compel us to ponder the origins, evolution, and ultimate destiny of the cosmos, merging scientific exploration with philosophical reflection. Cosmic processes reveal astonishing levels of interconnection. From the nuclear furnaces of stars that forge elements to the gravitational choreography shaping galaxies, we witness a universe governed by principles producing patterns and structures that can appear purposeful. Observing these phenomena inspires a sense of awe and even cosmic unity, illustrating that purpose can emerge not solely from conscious intent, but from the intricate dynamics of natural laws themselves. Evolution by natural selection exemplifies this. Over billions of years, life has produced complex organisms and ecosystems, seemingly guided by design, yet entirely without conscious oversight. Similarly, the behavior of matter and energy in physics, from conservation laws to thermodynamic tendencies, results in structured, predictable outcomes that shape the cosmos and create order without requiring intentionality. Human consciousness plays a central role in perceiving and attributing purpose. Our awareness enables us to seek patterns, explanations, and meaning, formulating complex ideas, scientific models, and philosophical frameworks. While the universe itself may lack intrinsic purpose, our reflections transform existence into a narrative, assigning significance where otherwise there is none. This cognitive impulse has propelled scientific discovery, technological innovation, and philosophical thought, expanding our understanding of both the cosmos and ourselves. The Big Bang Theory illustrates the intersection of cosmic origin and the question of purpose. According to this model, the universe emerged from an extraordinarily hot, dense state about 13.8 billion years ago, initiating expansion that would eventually produce galaxies, stars, and planets. While the theory describes the physical evolution of the cosmos, it remains silent on meaning or intent. Some interpret the finely tuned initial conditions as evidence of design, hinting at a potential underlying purpose. Others see the event as a natural phenomenon, remarkable yet devoid of conscious intent. Nevertheless, the unfolding sequence, from the first microseconds to the formation of stars and planets, from the chemical precursors of life to the emergence of sentient beings, offers a stage on which humanity can reflect upon its role. In contemplating the universe, humans may themselves become agents through which cosmic purpose is expressed, not as a directive imposed from above, but as a living awareness that finds significance within the vast, unfolding expanse of reality. This intricate interplay of natural law, emergent complexity, and human consciousness suggests that purpose in the universe is not a simple property to be discovered, but a dynamic phenomenon woven from the interaction of matter, energy, and awareness over billions of years. It is a story of a cosmos capable of generating life, a species capable of reflection, and a reality that, while indifferent to intent, becomes imbued with meaning through the minds of those who dare to ask, why? Ultimately, the connection between the Big Bang and the potential purpose of the cosmos remains a profound philosophical puzzle, one that bridges the divide between empirical science and the deepest existential inquiries. The Big Bang Theory lays out a scientific stage upon which these questions are projected, a framework that allows humanity to ponder its origins, its place in the universe, and the possibility of a greater cosmic design. Yet, the conditions that existed before the Big Bang remain among the most enigmatic frontiers in cosmology. As we approach that primordial moment, our current understanding of physics collapses, unable to describe with certainty what might have existed before the universe's explosive birth. Some theoretical models posit the existence of a singularity, a state of unimaginably high density and temperature where the laws of physics, as we know them, could cease to apply. Quantum fluctuations may have stirred within this pre-cosmic cauldron, perhaps igniting the expansion that gave rise to space, time, and the observable universe. Other hypotheses suggest that the Big Bang was not a unique event, but part of a vast multiverse, a sprawling ensemble of universes, each with its own birth, evolution, and perhaps distinct physical laws. While these ideas stretch the imagination and remain difficult to test with contemporary instruments, they expand the horizons of what we consider possible. Science, by its nature, does not directly grapple with purpose or meaning, since these concepts are not measurable or observable phenomena. Understanding the pre-Big Bang state, even in its entirety, may illuminate the mechanisms behind cosmic formation, but does not inherently reveal a purpose imbued in the universe. Nonetheless, this quest drives an unrelenting curiosity, pushing the boundaries of knowledge about space, time, and the fundamental fabric of reality. The laws of physics that emerged in the aftermath of the Big Bang form the backbone of the universe's ongoing evolution. Gravity, electromagnetism, and the strong and weak nuclear forces interact in a delicate balance, creating the conditions necessary for stars to ignite, galaxies to form, and planets to coalesce. The precision of these physical constants has led some scientists and philosophers to speculate about a deeper design underlying the cosmos. One remarkable feature of these laws is their universality. The same principles that govern the behavior of atoms in laboratories here on Earth also dictate the dynamics of stars and galaxies billions of light years away. This remarkable consistency across incomprehensible expanses of space and time hints at a fundamental order, a coherence that some interpret as indicative of intention or purpose. The fine-tuning of the cosmos extends to the parameters that allow for complex structures, including life itself. Even slight variations in fundamental constants could render the universe sterile, devoid of stars, planets, or the chemistry necessary for living organisms. This apparent fine-tuning has sparked extensive debate surrounding the anthropic principle, and whether our universe might simply be one of many in an expansive multiverse, where countless other universes exist with differing physical rules. Yet the presence of apparent design does not automatically imply a conscious creator or predetermined destiny. Many scientists argue that these conditions could emerge from random chance, from processes not yet fully comprehended, or from statistical inevitabilities in a cosmos far larger than our perception. Cosmic inflation represents a pivotal chapter in the story of the universe, describing a fraction of a second when the cosmos expanded at a rate faster than the speed of light. In this infinitesimal instant, the universe grew from subatomic dimensions to a scale larger than the observable universe today. This extraordinary expansion resolved lingering puzzles about the cosmos, explaining the uniformity of matter across vast distances, the flatness of space, and the absence of theoretical anomalies such as magnetic monopoles. Inflation also laid the groundwork for the formation of galaxies, clusters, and the intricate cosmic web. Quantum fluctuations, initially microscopic, were magnified to macroscopic scales, seeding the density variations that would become the scaffolding of cosmic structure. While inflation does not directly answer questions of purpose, it provides profound insights into the mechanics of the cosmos, suggesting that our observable universe may be a mere fragment of an unimaginably larger expanse. This leads naturally to considerations of the multiverse, a landscape where potentially infinite universes exist side by side, each following its own set of physical laws. The concept of multiple universes transforms our perspective on cosmic purpose. The apparent fine-tuning that makes life possible in our universe may not be exceptional, but inevitable in a multiverse of staggering proportions. With countless universes in play, the emergence of at least one hospitable to life becomes a matter of probability rather than miracle. The multiverse idea also opens the door to even more provocative notions: alternate versions of ourselves, living in parallel realities, making different choices, and experiencing divergent outcomes. This challenges our understanding of free will, determinism, and the very nature of existence. As humanity peers ever deeper into the origins and structure of the cosmos, the boundary between physics and philosophy blurs, inviting us to confront both the mechanisms and the meaning of our existence. The quest to understand the universe, from the singularity that may have preceded the Big Bang to the possibility of countless other universes beyond our own, is a journey without end, a testament to the enduring drive to comprehend our place in a vast, enigmatic, and awe-inspiring cosmos. Ultimately, the multiverse theory urges us to push the limits of imagination and contemplation, to venture far beyond the familiar boundaries of our observable universe, and envision an incomprehensibly vast cosmic tapestry. It challenges us to grapple with questions of existence, purpose, and meaning on scales so immense that the mind strains to comprehend them, prompting a fusion of philosophical reflection and scientific inquiry that stretches the very edges of human understanding. The concept that our universe had a distinct beginning is supported by a remarkable convergence of evidence. Perhaps the most striking of these is the expansion of the universe, first observed by Edwin Hubble in the 1920s. Hubble discovered that galaxies are not stationary. They are moving away from us, and the more distant a galaxy is, the faster it recedes. Tracing this motion backward in time suggests a moment when all matter and energy were concentrated at a single unimaginably dense point, a singularity from which the cosmos sprang. Complementing this is the discovery of the cosmic microwave background radiation, accidentally detected by Arno Penzias and Robert Wilson in 1964. This faint, omnipresent glow is the afterglow of the Big Bang, its properties perfectly aligning with theoretical predictions and offering a compelling testament to a universe with a definite origin. Further evidence comes from the abundance of light elements, particularly hydrogen and helium, whose observed ratios match predictions from nucleosynthesis during the universe's infancy. This agreement between observation and theory reinforces the case for a beginning marked by extreme energy and density. Additionally, the intricate distribution of galaxies and large-scale cosmic structures reflects patterns expected from gravitational evolution following the Big Bang. Sophisticated computer simulations accurately recreate this cosmic web, where clusters of galaxies and immense voids align with models of early matter distribution, underscoring the universe's origin in a singular event. The initial conditions set in the universe's first moments are crucial in shaping its evolution and potential purpose. These primordial parameters, the distribution of matter and energy, the relative strength of fundamental forces, and the laws of physics themselves, function as a blueprint directing cosmic development. Remarkably, certain constants and ratios appear finely tuned to permit the formation of complex structures, stars, galaxies, and eventually life. This apparent precision provokes profound philosophical questions about whether the universe's fabric inherently favors complexity and consciousness, suggesting a possible underlying cosmic intent. These early conditions also influence the universe's destiny. The delicate balance between the expansion rate and gravitational pull determines whether the cosmos will expand indefinitely, collapse, or reach a steady state. The distribution of matter forms a scaffolding for galaxies, clusters, and cosmic voids, creating a framework that allows for increasing complexity and potentially conscious life. The universe, in this sense, may be following a path laid out from its very beginning, its ultimate trajectory written into the laws of physics themselves. While the Big Bang theory remains the dominant paradigm, alternative models provide different lenses for considering cosmic origins. The steady-state theory posits a universe without beginning, continuously expanding with matter emerging to maintain constant density. The cyclic universe model imagines endless sequences of expansion and contraction, where the Big Bang represents one of countless cosmic rebirths, each potentially lasting trillions of years. The holographic universe theory offers an even more radical perspective, proposing that our three-dimensional reality is a projection of information stored on a two-dimensional surface, challenging perceptions of reality and raising questions about consciousness and existence itself. These alternatives reshape our understanding of cosmic purpose. The cyclic model implies multiple histories and futures, suggesting diverse forms of life and consciousness may emerge across vast timescales. The holographic model hints that reality itself may be an emergent phenomenon, a sophisticated illusion shaped by fundamental informational structures. Through these lenses, the universe is less a singular event and more an ongoing, evolving process, where meaning may arise from complex interactions of matter, energy, and conscious observers over time. Quantum fluctuations, the microscopic irregularities emerging from the uncertainty inherent in quantum mechanics, played a critical role in forming the universe's structure. These tiny variations in the first fractions of a second after the Big Bang grew under gravity's influence, seeding galaxies, stars, and planets. While quantum mechanics itself implies no inherent purpose, the fact that these fluctuations enabled conditions conducive to life sparks reflection on whether the universe exhibits a subtle bias toward complexity and consciousness. Some interpret this through the anthropic principle. We observe such conditions because only in a universe capable of producing observers could these questions arise. The early universe offers profound insight into its potential fate and underlying principles. The expansion of space accelerating over time suggests a cosmos that may grow indefinitely, leading toward a big freeze, where matter becomes isolated, stars burn out, and energy dissipates. Observing these phenomena provides a glimpse of the vast unfolding narrative of existence, a story written in the fabric of space and time itself, stretching from a singular beginning toward an uncertain, awe-inspiring future. Through this lens, our universe is a dynamic, evolving entity, a stage for phenomena as grand as galactic clusters and as minute as quantum fluctuations, weaving a story of origin, growth, and potential purpose that transcends imagination and invites us to ponder our place in an ever-expanding cosmic tapestry. However, the ultimate destiny of the universe remains an enigma, an unfolding mystery written in the very fabric of space and time. From the moment of its fiery birth, the conditions set in place, the delicate arrangement of matter and the ebb and flow of energy, began a complex dance that continues to shape its vast evolution. The revelation of dark energy, an invisible and enigmatic force propelling the universe to expand ever faster, has only deepened the puzzle, complicating our projections and forcing cosmologists to confront the limits of our understanding. Questions of purpose linger beyond the reach of empirical science, yet the astonishing precision of physical constants and the emergence of intricate cosmic structures from primordial simplicity continue to spark both scientific inquiry and philosophical reflection, nudging humanity to ponder our place within this immense cosmic tapestry. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, serve as the backbone of the cosmos, orchestrating the interplay of matter and energy across all scales. Each force, operating in its unique domain, contributes to the evolution of the universe from a searing, dense beginning to the complex, structured expanse we observe today. Gravity, the most far-reaching yet weakest of these forces, exerts its influence over the vast cosmic stage, gathering matter into galaxies, stars, and planets. It molds the very scaffolding upon which complex structures arise, providing the arenas where chemistry, geology, and life itself can unfold. Electromagnetism governs interactions among charged particles, binding electrons to atomic nuclei to form atoms, molecules, and ultimately the chemical frameworks essential for life. The strong nuclear force binds quarks together, forming the protons and neutrons that make up atomic nuclei. And through this binding, it becomes the silent architect of matter's stability. This force fuels the nuclear reactions at the heart of stars, forging the elements that seed planets and enable life. Its finely tuned strength is extraordinary. A slight deviation could either prevent the formation of stable nuclei or cause all matter to collapse into a singular supernucleus, illustrating a cosmic balance that has led to the universe's rich complexity. Meanwhile, the weak nuclear force operates subtly, governing specific types of radioactive decay and driving the nuclear processes within stars. It powers the fusion of hydrogen into helium, sustaining stars like our Sun for billions of years, and disperses heavy elements into space through supernova explosions, elements crucial for the creation of planets and life. Without this force, the universe would be a cold, inert expanse, devoid of the energy and materials necessary for complexity to arise. Gravity, in its grand role as cosmic architect, shapes the universe's large-scale structure. It pulls matter into dense clusters, forming galaxies and galaxy clusters connected by filaments of gas and dark matter, creating an intricate cosmic web. Voids, vast, nearly empty regions, emerge as gravity amplifies differences in density over eons. Within galaxies, gravity binds stars into coherent systems, and the unseen pull of dark matter adds further cohesion to these enormous structures. Yet gravity is locked in perpetual tension with dark energy, the mysterious force accelerating the expansion of space itself, a dynamic that will ultimately influence the universe's long-term fate and shape. The strong nuclear force continues to define the microscopic architecture of matter, ensuring that protons and neutrons remain bound within atomic nuclei. It allowed quarks to coalesce into hadrons shortly after the Big Bang, establishing the foundation for the first atomic nuclei and enabling subsequent stellar fusion processes that produce heavier elements. This intricate balance, where even a minuscule change in force strength could disrupt the universe's fabric, invites reflection on the possibility of a deeper order or design underlying existence. The weak nuclear force, though less visible, sustains the processes that power stars and drive element formation. It orchestrates the reactions that convert hydrogen to helium in stellar cores, supports supernovae that scatter life-essential elements, and ensures that stars shine long enough to provide stable conditions for planets and life to flourish. Electromagnetism shapes both the microcosm and the cosmos, binding atoms into molecules, enabling chemical reactions, and governing the behavior of stars. Within stellar cores, electromagnetic forces counterbalance gravitational collapse, allowing stars to shine steadily for billions of years, producing the light and warmth necessary for life. Electromagnetic radiation, visible light, radio waves, X-rays, travels across the universe, carrying with it the history of cosmic evolution. The faint glow of the cosmic microwave background, a relic from the Big Bang, offers a window into the universe's earliest moments, allowing humanity to trace its expansive journey across space and time. Together, these four forces weave the complex web of existence. Their delicate interplay has transformed a simple, hot, dense beginning into a universe teeming with structure, complexity, and the potential for consciousness. While science may not define a cosmic purpose, the universe's intricate architecture, the emergence of stable matter, and the conditions enabling life suggest an extraordinary unfolding, an expansive narrative in which the cosmos itself becomes a stage for observation, understanding, and awe. The balance of these forces, from the atomic to the cosmic scale, is a testament to the universe's capacity to generate order, diversity, and the profound phenomena that give rise to stars, planets, and living beings capable of marveling at their own origins. Furthermore, electromagnetism might play a pivotal role in the universe's potential purpose by providing the precise conditions necessary for complexity to emerge, ultimately enabling conscious beings to arise. The intricate ballet of electrons within biological systems, guided by electromagnetic forces, allows living organisms to store, transmit, and process information with astonishing efficiency. This delicate orchestration of atomic and molecular interactions hints at electromagnetism as a fundamental enabler of intelligence and self-awareness across the cosmos, suggesting that the universe's very structure could be tuned to foster the emergence of life capable of reflection and understanding. Dark energy, an elusive and mysterious force, permeates every corner of space, driving the expansion of the universe and accelerating it at a pace that continues to astonish scientists. Accounting for roughly 68% of the universe's total energy, dark energy remains one of the most profound enigmas in modern cosmology. As galaxies and clusters of galaxies drift ever farther apart, this invisible force appears to strengthen, exerting an increasing influence on the evolution of cosmic structures. Its relentless push against gravity hints at a universe that may expand indefinitely, potentially leading to a distant future in which galaxies are so widely separated that they fade from view, leaving vast stretches of emptiness. Dark energy challenges the limits of human understanding, questioning fundamental physical principles and the ultimate fate of the universe. Some researchers speculate that it might be an inherent property of space itself, manifesting as a form of negative pressure that grows as the cosmos expands. Regarding the universe's potential purpose, the role of dark energy invites both scientific scrutiny and philosophical reflection. While science refrains from attributing conscious intent to cosmic phenomena, the discovery of dark energy inevitably sparks contemplation about whether the universe's expansion could serve a function or purpose beyond human comprehension. Nevertheless, many caution against interpreting natural forces as purposeful, emphasizing that the behavior of dark energy is more accurately understood through physical laws than through teleological reasoning. Dark matter, another invisible and enigmatic substance, exerts a profound influence on the universe's structure. Unlike ordinary matter, it neither emits nor absorbs light, yet its gravitational effects are immense. In the formation of galaxies, dark matter acts as a cosmic scaffold, establishing deep gravitational wells that attract ordinary matter. In the early universe, regions with slightly higher concentrations of dark matter pulled in more gas and dust, eventually giving rise to the stars and galaxies we observe today. Without dark matter, the cosmos would be markedly different, with matter more evenly dispersed and fewer large-scale structures. On a grander scale, dark matter weaves an intricate cosmic web that spans the universe, consisting of dense filaments and nodes where galaxies and clusters congregate, interspersed with vast, nearly empty voids. This cosmic web directs the flow of matter and energy across space, influencing the distribution, movement, and formation of galaxies. The gravitational influence of dark matter also explains the unexpectedly rapid rotation of galaxies' outer regions, providing the additional pull needed to hold galaxies together and shape their sizes and forms. As researchers continue to probe these hidden realms, our understanding of dark matter and its essential role in cosmic architecture deepens, offering glimpses into the universe's underlying framework. The cosmic web represents the largest known structure in the universe, an immense network of interconnected filaments composed of dark matter and galaxies, stretching across billions of light years. Enormous voids punctuate this web, accentuating its sponge-like structure. This grand architecture arises from the interplay of gravity and cosmic expansion, with minute density variations in the early universe gradually amplified over billions of years, drawing matter toward denser regions and leaving other areas increasingly empty. The resulting sponge-like pattern preserves a record of the universe's infancy, offering scientists a window into conditions that existed long before the first stars ignited. By examining these structures, researchers gain insights into dark matter, dark energy, and the fundamental forces that have sculpted the cosmos. Although the cosmic web does not explicitly reveal a universal purpose, its regularity and adherence to physical principles suggest an underlying order, hinting at structures and processes that humanity is only beginning to comprehend. The cosmic web's immense scale and complexity compel reflection on our place within the universe, revealing a tapestry of staggering intricacy that extends far beyond human perception. Galaxy clusters and superclusters further illuminate the grandeur of the universe's architecture. These colossal assemblies of thousands of galaxies, bound together by gravity, serve as markers of the cosmos's underlying structure. Individual clusters, often spanning millions of light years, contain not only luminous matter, but also vast reservoirs of dark matter and superheated gas. Studying the dynamics within these clusters allows scientists to infer the distribution of visible and invisible matter across the universe. On an even grander scale, superclusters consist of numerous galaxy clusters stretching across hundreds of millions of light years. These sprawling formations outline the cosmic web, revealing a large-scale structure shaped by initial quantum fluctuations, amplified over billions of years through gravitational forces. Mapping and analyzing these immense systems provides critical evidence for the presence of dark matter and dark energy, refining models of cosmic evolution and expansion. The distribution and motion of galaxy clusters and superclusters illuminate the forces that govern the universe's growth and transformation, offering insights not only into the past, but also into the potential trajectories of its future. This layered structure of matter, from the microscopic interactions of electrons to the vast cosmic web, paints a picture of a universe that is at once incomprehensibly immense and finely tuned. A complex and dynamic system whose evolution continues to challenge and inspire human understanding. The distribution of matter across the cosmos reveals a tapestry of staggering complexity, weaving together galaxies, clusters, and immense filaments that stretch across incomprehensible distances, separated by vast voids that seem almost impossibly empty. But drawing conclusions about a deeper purpose embedded in this arrangement demands careful reflection and precision. On the grandest scales, the universe takes on the appearance of a cosmic web, its intricate filaments tracing the paths where galaxies cluster together, shaped over billions of years by the invisible hands of gravity, acting on infinitesimal quantum fluctuations present in the primordial universe. What is astonishing is how closely this vast architecture mirrors the predictions of modern computer simulations, each line of code reflecting our understanding of the physical laws that govern reality. Underlying this structure is the elusive presence of dark matter, inferred only through its gravitational influence, yet exerting an invisible but profound role in guiding the formation of galaxies and orchestrating the grand design of cosmic structures. The uniformity of this matter across immense expanses reinforces the cosmological principle, which posits that the universe appears roughly the same no matter the vantage point. This remarkable homogeneity implies that no single location in the universe holds any special significance, challenging the notion that the cosmos has a central or intentional purpose tied to a particular region. What we observe instead is a universe governed by natural processes unfolding over unimaginable spans of time. As astronomers and physicists probe ever deeper into the cosmos, they uncover layers of complexity and order that speak to the elegance of physical laws, even if questions of ultimate purpose remain within the realm of philosophy rather than empirical science. Stars emerge as central actors in this cosmic narrative, their existence and life cycles shaping both the material and experiential fabric of the universe. These incandescent furnaces are the forges of the cosmos, performing the alchemical process of stellar nucleosynthesis, through which simple elements like hydrogen are fused into helium, and in larger stars, progressively heavier elements from carbon and oxygen up to iron. When massive stars reach the cataclysmic end of their lives as supernovae, these elements are violently expelled into the surrounding space, seeding the interstellar medium with the raw ingredients for planets, complex molecules, and ultimately, life itself. Through this continuous cycle of birth, life, and death, stars act as cosmic engines of complexity, converting simplicity into the intricate diversity of matter we observe today. Beyond their material contributions, stars illuminate the universe, their radiant energy carrying information across unimaginable distances. By studying starlight, scientists decode the chemical composition, age, and evolutionary histories of galaxies billions of light years away, piecing together the grand story of the cosmos. In this way, stars indirectly facilitate the emergence of observers, beings capable of contemplating and understanding the universe itself, making them not only architects of material complexity, but also enablers of cosmic consciousness. The process of stellar nucleosynthesis exemplifies the interconnectedness of all cosmic matter. The first generations of stars, composed almost entirely of hydrogen and helium, produced heavier elements and scattered them through explosive deaths, enriching the material that would form subsequent generations of stars, planets, and eventually life. Every atom in our bodies, from the carbon in our cells to the iron in our blood, was once forged in the heart of a star long extinguished, linking us inextricably to the grand narrative of the universe. This evolutionary progression, from simplicity to complexity, from hydrogen clouds to conscious beings capable of reflection, underscores the astonishing capacity of natural processes to generate conditions conducive to life and understanding without necessitating any preordained purpose. Stars are, in essence, the engines of cosmic evolution, Born in massive clouds of hydrogen and helium, ignited by the crushing force of gravity that sparks nuclear fusion, they create the elements that constitute the universe. As they age, stars progress through phases that culminate in either quiet fading or dramatic supernova explosions, redistributing their elemental bounty to the surrounding space. This recycling of matter fuels the formation of new stars and complex structures, establishing a continuous cycle of creation and transformation. In this light, stellar evolution demonstrates the remarkable interconnectedness of the cosmos, where even the violent death of a star contributes to the birth of new worlds and the potential emergence of life. Supernovae in particular act as cosmic catalysts, shaping the chemical and structural evolution of the universe. These stellar detonations release titanic amounts of energy, forging elements heavier than iron, gold, uranium, and others, and scattering them across space. The shock waves from these explosions compress nearby clouds of gas and dust, initiating the formation of new stars and perpetuating the ongoing cycle of cosmic renewal. Through these processes, the universe exhibits a self-organizing tendency, generating increasing complexity over time, and laying the groundwork for conscious observers capable of exploring and reflecting on the cosmos. In the interplay of stellar birth, fusion, and explosive death, we witness a universe that evolves according to natural laws, producing the raw materials and conditions necessary for planets, life, and intelligence. While the universe may not possess a predetermined purpose in the traditional sense, the patterns and processes it follows suggest a remarkable coherence and a capacity to create conditions for its own exploration. The story of matter and stars is one of transformation, resilience, and emergence, connecting the smallest atoms to the vast cosmic web and linking human consciousness directly to the legacy of stars that have long since burned out. Through these ceaseless cycles, the universe demonstrates its power to evolve, to generate complexity, and to provide the conditions necessary for beings capable of contemplating their own place within it. Furthermore, supernovae act as cosmic signposts, illuminating the vast expanses of the universe and allowing astronomers to gauge distances that span billions of light years. Among these stellar explosions, Type E supernovae hold a unique significance due to their remarkably consistent luminosity. This uniform brightness makes them reliable standard candles, essential tools for measuring the scale of the cosmos. Observations of these stellar beacons have led to paradigm-shifting revelations, including the discovery that the universe is not merely expanding, but doing so at an accelerating rate. This acceleration implies the existence of an enigmatic force known as dark energy, a component that profoundly shapes our understanding of cosmic evolution and the ultimate fate of the universe. Galaxies themselves emerge through a delicate interplay of gravitational forces and the unfolding story of cosmic evolution. In the universe's infancy, tiny fluctuations in matter density created regions of slightly greater mass, which in turn exerted a stronger gravitational pull. Over millions of years, these regions gradually amassed more matter, growing denser and larger. As these embryonic galactic regions expanded, they began to rotate due to the conservation of angular momentum, forming sprawling disks of gas and dust. Within these vast, rotating structures, pockets of material collapsed under their own gravity, igniting nuclear fusion and giving birth to the first generations of stars. These stellar nurseries continued to seed the cosmos with new stars, while older stars enriched the interstellar medium with heavier elements through the dramatic explosions of supernovae. Across billions of years, this ongoing cycle of star formation and destruction sculpted the intricate, diverse structures we now observe in galaxies. The story of galaxy formation highlights the universe's capacity for increasing complexity and organization. From primordial hydrogen and helium, the cosmos has fashioned intricate systems capable of supporting life. This progression raises profound philosophical questions, hinting at the potential for the universe to create environments where conscious beings can emerge and reflect on their own existence. Yet, attributing purpose to these processes remains a matter of interpretation, a philosophical perspective rather than a scientific assertion. What remains indisputable is the astonishing ability of fundamental physical laws to orchestrate order on a grand scale, producing vast, organized structures from the raw material of the cosmos, inviting us to ponder our place within this immense, ever-evolving universe. Galactic collisions further illustrate the dynamic nature of the cosmos, acting as catalysts in the evolution of galaxies. When two or more galaxies approach one another closely enough for their gravitational fields to interact, they engage in slow, intricate dances that unfold over millions or even billions of years. These encounters, contrary to the violent imagery their name suggests, trigger profound transformations. Gas clouds within the colliding galaxies are compressed, igniting bursts of star formation that can give rise to some of the most massive and luminous stars in existence. Such mergers also play a crucial role in feeding and growing supermassive black holes at galactic centers. As interstellar material funnels toward the cores, these colossal black holes accrete matter, often resulting in periods of intense activity known as active galactic nuclei. The physical structure of galaxies is also reshaped through these cosmic interactions. Spiral galaxies may evolve into elliptical galaxies after major mergers, while long tidal tails of stars and gas stretch far beyond the primary bodies, creating fossilized remnants of past collisions. These features provide astronomers with a historical record, enabling them to trace the evolutionary pathways of galaxies and understand the broader development of cosmic structures. Supermassive black holes, with masses ranging from millions to billions of times that of our Sun, exert a gravitational influence that extends across entire galaxies and beyond. Their enormous mass forms deep gravitational wells, governing the motion of stars, gas, and dust, and maintaining the structural integrity of the galactic bulge. Beyond their gravitational pull, these black holes drive energetic outflows, releasing immense quantities of energy as matter spirals into their accretion disks. These active galactic nuclei can launch jets of particles and radiation across intergalactic space, heating surrounding gas and regulating star formation by preventing cooling and collapse. In this way, supermassive black holes are not mere cosmic curiosities, but fundamental architects of galactic evolution, shaping the distribution of matter and influencing the life cycles of countless stars across the universe. Furthermore, when galaxies collide and merge, the cosmic ballet extends to their very cores, where supermassive black holes, the enigmatic engines of gravity, combine in a titanic union. This cosmic merger sends ripples through spacetime itself, known as gravitational waves, faint yet detectable echoes of unimaginable energy traveling across the universe. And these galactic collisions are far from mere accidents. They are essential mechanisms in the universe's grand design, enabling smaller galaxies to be absorbed into larger ones and gradually building the colossal galaxies and sprawling galaxy clusters that dominate the cosmic landscape today. The intimate dance between supermassive black holes and their host galaxies drives the evolution of the universe's structure, shaping the vast cosmic web of galaxies, filaments, and yawning voids that stretch across the universe, mapping the skeleton of our cosmos. The Milky Way itself serves as a profound testament to these forces, offering a window into the complex interplay of cosmic evolution without claiming to answer why the universe exists. This immense spiral galaxy, an intricate swirl of stars, gas, and dust, spans more than 100,000 light-years from edge to edge. Its composition reads like a ledger of cosmic history, chronicling billions of years of star formation and the gradual creation of chemical elements. Anchoring this celestial metropolis is a supermassive black hole, a gravitational titan around which a dense bulge of older stars coalesces. From this heart, the galaxy's spiral arms unfurl, vibrant highways hosting younger stars, luminous nebula, and concentrated pockets of star birth, where the cycle of creation continues with relentless precision. The variety of stellar ages across the Milky Way paints a vivid picture of ongoing cosmic cycles, of birth, life, and death, played out over epochs measured in billions of years. The elements scattered throughout our galaxy tell a deeper story of cosmic alchemy. In the universe's infancy, hydrogen and helium dominated, yet successive generations of stars have forged heavier elements through the furnace of nuclear fusion and the explosive death throes of supernovae. Iron, carbon, oxygen, and countless others were born in these stellar crucibles, dispersed into interstellar space to seed future stars, planets, and eventually, life itself. Examining the Milky Way's structure and chemical makeup illuminates fundamental cosmic principles. The omnipresence of gravity shaping galactic formations, the intricate life cycles of stars, and the creation and distribution of the very elements that make life possible. Though these observations cannot provide an ultimate purpose, they reveal the staggering complexity and interwoven nature of the cosmos, a universe both structured and dynamic. Beyond the bustling neighborhoods of galaxies lie the vast intergalactic voids, immense regions largely empty of stars and galaxies, stretching across hundreds of millions of light years. These colossal cosmic deserts, seemingly barren, play a critical role in our understanding of universal structure and evolution. They act as the negative imprint of the cosmic web, emphasizing the absence of matter in contrast to the dense filaments and clusters. By studying these voids, astronomers gain insight into how matter is distributed on the largest scales, refining models of cosmic evolution and the formation of large-scale structures. Voids serve as natural laboratories, where the behavior of sparse galaxies can illuminate the elusive nature of gravity and dark energy. Observing how voids expand over time provides essential clues about the universe's accelerating expansion. The few galaxies that do inhabit these regions offer lessons about the influence of environment on galactic development, revealing alternative paths of formation and evolution that challenge conventional understanding. Equally ancient are globular clusters, dense, spherical collections of stars that orbit the centers of galaxies, some nearly as old as the universe itself. These stellar relics serve as cosmic time capsules, preserving information about the early universe's chemical composition and the epochs of star formation. By examining these clusters, scientists can trace the evolution of elements, stellar populations, and galactic dynamics across billions of years. Globular clusters also interact with their host galaxies, influencing their structure and potentially feeding stars towards central supermassive black holes, contributing to their growth. In these clusters, astronomers explore the physics of extreme conditions, the distribution of dark matter, and the processes governing stellar evolution, making globular clusters vital windows into the workings of the cosmos and the forces that have shaped it since its earliest moments. Planet formation represents another crucial thread in this cosmic tapestry, illustrating the universe's capacity for creating complexity from simplicity. Around nascent stars, clouds of gas and dust coalesce, forming rocky terrestrial worlds and vast gas giants, a process repeated across countless systems. Planetary formation does more than sculpt celestial landscapes. It creates potential habitats where chemistry can advance toward life. Earth itself stands as evidence of these processes, a testament to how the universe's natural tendencies can give rise to conditions suitable for living organisms. The discovery of thousands of exoplanets orbiting distant stars confirms that planet formation is widespread, suggesting that the ingredients for life may be a recurring theme throughout the galaxy. Each new planet discovered, each orbit mapped, reinforces the narrative of a universe adept at constructing intricate structures from the raw materials scattered across space, hinting at the profound possibilities embedded in the cosmic order. Moreover, the formation of planets represents a remarkable chapter in the ongoing story of the universe's increasing complexity. In the moments following the Big Bang, the cosmos was a relatively simple expanse, dominated by hydrogen, helium, and trace amounts of other elements. Over billions of years, gravitational forces orchestrated the condensation of matter into stars, galaxies, and eventually planetary systems. Planets, emerging from the swirling disks of gas and dust around young stars, introduced entirely new layers of complexity. These celestial bodies are not static. They host intricate processes such as atmospheric circulation, weather patterns, volcanic activity, and tectonic shifts. In some cases, they may even provide conditions suitable for biological evolution, adding a dimension of life to an already intricate cosmic tapestry. Although the ultimate purpose of the universe remains elusive, the widespread occurrence of planet formation hints that the creation of stable, life-sustaining environments may be a natural consequence of cosmic evolution. This perspective casts humanity not merely as observers of the cosmos, but as participants in a grand, ongoing process of cosmic creativity, exploration, and transformation. For a planet to potentially harbor life in a form recognizable to us, it must meet a complex set of conditions. Foremost among these is location. The planet needs to reside in the habitable zone of its star, often called the Goldilocks zone. This region is neither too hot nor too cold, allowing for the presence of liquid water on the planet's surface, a critical ingredient for life. Beyond this, a stable atmosphere is essential. Such an envelope of gases moderates temperature, shields the surface from harmful stellar radiation, and supplies vital components for biological processes, including carbon dioxide, nitrogen, and oxygen. A protective magnetic field further enhances habitability, deflecting charged particles and preserving the atmosphere against erosion. The internal composition of the planet also plays a pivotal role. A rocky core and sufficient mass are necessary to sustain geothermal heat, which drives mantle convection and plate tectonics. These geological processes stabilize the climate over geological timescales by regulating carbon cycles and recycling essential minerals. Equally important is the availability of organic compounds and essential chemical elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which form the building blocks of life. These factors together create a delicate balance, a cosmic recipe for the emergence of living systems. While these criteria are derived from the study of Earth, they provide a foundational framework for exploring life elsewhere in the universe. The concept of habitable zones intersects intriguingly with questions of cosmic purpose. These regions around stars, where conditions are just right for liquid water, ignite profound inquiries into whether the universe is predisposed toward life. Some scientists suggest that habitable zones are statistical inevitabilities in a vast cosmos, an outcome of chance rather than design, aligning with the principle of mediocrity, which posits that Earth and its inhabitants are not inherently unique. Others view these zones as tantalizing hints of a deeper cosmic intention, a subtle suggestion that the universe may harbor countless worlds capable of supporting life. In recent decades, astronomers have discovered numerous exoplanets within their stars' habitable zones, fueling speculation about extraterrestrial life. Yet the existence of these zones, while promising, does not resolve the philosophical debate over whether life is a cosmic accident or part of a larger pattern woven into the fabric of the universe. Gas giants, the colossal planets composed predominantly of hydrogen and helium, further illustrate the dynamic forces that shape planetary systems. Their immense gravitational pull profoundly influences the orbits and development of neighboring bodies. One of their most crucial roles is acting as cosmic guardians, attracting or deflecting comets, asteroids, and other potentially catastrophic objects that could threaten inner rocky planets. This protective function may have been essential for life on Earth, preventing frequent, large-scale impacts during the early solar system that could have extinguished nascent life. Gas giants also participate actively in planetary formation. Their gravitational fields can migrate within their systems, disrupting the orbits of smaller objects and redistributing material, which affects the architecture of entire solar systems. By altering the flow of gas and dust in the protoplanetary disk, these giants influence which materials are available for the formation of terrestrial planets, subtly shaping their composition, size, and potential for habitability. The interactions between gas giants and their surroundings exemplify the complex choreography that governs planetary evolution, revealing a system of cause and effect that spans billions of years. Asteroid and comet impacts add yet another layer of influence on planetary development. These high-energy collisions have sculpted surfaces across the solar system, leaving craters on Mercury, the Moon, and countless other celestial bodies. On Earth, they have had transformative effects on the trajectory of life itself. The most iconic example, the Chicxulub impact, approximately 66 million years ago, wiped out the dinosaurs and enabled mammals to rise to dominance. Yet these events are not solely destructive. They also deliver essential materials, including water and organic molecules, which may contribute to the conditions necessary for life. The relentless bombardment of planetary surfaces throughout cosmic history has been a catalyst for both destruction and creation, highlighting the intricate interplay between chance, physics, and biological potential in shaping worlds. However, impacts have not solely been agents of destruction in the vast theater of the cosmos. Some researchers propose that comets and asteroids, those wandering celestial travelers, may have delivered essential water and complex organic molecules to the infant Earth, seeding the primordial environment with the ingredients necessary for life to arise. Beyond the boundaries of our own planet, these cosmic collisions continue to sculpt and redefine the landscapes of other worlds. On Mars, colossal impact basins like Gila's Planitia have dramatically reshaped the planet's geology, carving immense depressions and influencing the thin Martian atmosphere, leaving marks that speak to a turbulent history spanning billions of years. Similarly, the relentless bombardment of Jupiter's moon Europa constantly fractures its icy shell, opening pathways through which materials from the hidden subsurface ocean below can surface, creating conditions that may be conducive to life in one of the coldest corners of our solar system. These impacts are not merely destructive, they are also storytellers. By examining the craters and their surrounding formations, scientists extract crucial clues about the composition, age, and evolution of planetary bodies. Each scar on a planet's surface is a chapter of cosmic history, revealing insights into planetary formation, the migration of celestial objects, and the dynamism that shapes worlds over eons. Such knowledge extends our understanding beyond Earth, guiding the search for potentially habitable planets in distant star systems. Exoplanets, those myriad worlds orbiting stars beyond our sun, hold a treasure trove of information about life's potential elsewhere in the universe. Each discovery expands our understanding of planetary diversity, revealing environments that range from gas giants many times the size of Jupiter to rocky Earth-like spheres. The sheer number of exoplanets uncovered thus far underscores that planets are a common feature of the cosmos, amplifying the probability that some may harbor conditions favorable to life. Scientists focus on exoplanets within the so-called habitable zones of their stars, regions where temperatures could permit liquid water to exist, a fundamental requirement for life as we comprehend it. By analyzing exoplanetary atmospheres, researchers can detect chemical signatures such as water vapor, methane, and other organic compounds, suggesting the possibility of biological processes occurring light years away. Yet exoplanets also illuminate the singularity of Earth. While many worlds exist within habitable zones, a confluence of factors, ranging from a stable atmosphere and a protective magnetic field to active geology, renders Earth uniquely suitable for sustaining life. By comparing these distant planets to our own, scientists refine their understanding of the conditions necessary for true habitability and enhance the precision of the search for extraterrestrial life. Planetary migration plays a pivotal role in shaping solar systems and influencing the emergence of life. As planets drift from their original orbits, they can radically transform the environments of neighboring worlds, producing both opportunities and challenges for the development of life. When massive gas giants migrate inward, they can push smaller rocky planets closer to their star, or even eject them from the system entirely. Such movements can place potentially habitable worlds within the so-called Goldilocks zone, where temperatures allow liquid water to persist, or conversely thrust them into inhospitable extremes, too cold for life to flourish. Migrating planets also dictate the flow of water and organic compounds throughout a system, scattering comets and asteroids that may deliver life's essential building blocks, or alternatively, subject worlds to catastrophic bombardment that sterilizes their surfaces. The gravitational influence of these wanderers can generate tidal heating in smaller moons or planets, fostering hidden subsurface oceans in regions otherwise frozen solid. Such environments, like those speculated to exist beneath the icy crusts of Jupiter's and Saturn's moons, could harbor the rudimentary conditions for life, undetected, yet teeming beneath layers of ice. Moons themselves play an equally vital role in creating and sustaining life-friendly environments. These natural satellites can stabilize a planet's axial tilt, generating consistent seasons and climates that support the evolution of complex ecosystems. Earth's own moon is instrumental in maintaining the planet's axial balance, fostering the stable climate that has allowed life to flourish. Beyond this, tidal forces exerted by moons can heat interiors through friction, sustaining liquid water beneath frozen surfaces. Europa exemplifies this phenomenon, harboring a subsurface ocean beneath its icy shell, despite the moon's bitterly cold exterior. In these hidden oceans, shielded from the harshness of space, microbial life could potentially emerge, demonstrating that the universe's most inhospitable appearances can conceal life-bearing possibilities. Through these interconnected processes, from asteroid impacts and planetary migrations to the stabilizing influence of moons, the cosmos reveals a dynamic, ever-evolving landscape in which life is neither guaranteed nor random, but arises under precise, intricate conditions. Every collision, every orbital shift, every icy moon and distant exoplanet contributes to the grand narrative of life, illustrating the delicate balance that allows existence to persist amid the immense, often violent expanse of the universe. Furthermore, moons play an essential role in safeguarding their parent planets, acting as silent sentinels in the vast expanse of space. By drawing in and absorbing a portion of the countless fragments of cosmic debris that constantly traverse the solar system, moons can prevent these potentially catastrophic objects from colliding with their planets. This gravitational shielding offers a subtle but profound protection, reducing the frequency of planet-wide catastrophes and creating a more stable environment where life has the opportunity to emerge, adapt, and flourish over eons without constant interruptions. The presence of a moon, therefore, is more than just a celestial adornment. It can be a critical factor in the delicate balance that allows life to gain a foothold and evolve complex ecosystems. Equally vital in this cosmic defense are planetary magnetic fields, invisible yet powerful shields born deep within the heart of planets. These magnetic fields arise from the dynamo effect, a remarkable process that occurs when a planet rotates, stirring electrically conductive fluids within its molten core. This movement generates immense electric currents, which in turn give rise to magnetic fields that stretch far beyond the planet's surface, creating protective envelopes that reach into space itself. These magnetic fields act as barriers, deflecting high-energy particles from solar winds and cosmic rays, particles that, if unimpeded, could wreak havoc on delicate organic molecules and nascent life forms. In addition to shielding life from radiation, these fields help prevent the erosion of a planet's atmosphere, preserving the conditions necessary for sustaining life. Earth exemplifies the protective power of a strong magnetic field. For billions of years, it has served as a cosmic guardian, deflecting destructive radiation and enabling life to evolve undisturbed. Mars, by contrast, suffered an early loss of its global magnetic field, which left its atmosphere vulnerable to relentless solar winds. Over time, this gradual stripping of the Martian atmosphere diminished the planet's capacity to sustain liquid water on its surface, rendering it far less hospitable. The presence, strength, and stability of a planetary magnetic field, therefore, can emerge as crucial determinants in the quest to identify potentially habitable worlds beyond our solar system. Astrobiologists actively consider this factor when evaluating exoplanets, viewing a robust magnetic field as a vital indicator of long-term habitability. Life's resilience on Earth provides a roadmap for imagining the possibilities elsewhere in the cosmos. Extremophiles, organisms that thrive in conditions once thought uninhabitable, illuminate the astonishing adaptability of life. Some flourish in scorching heat, others endure freezing cold, crushing pressure, or highly acidic and saline environments. These organisms challenge our assumptions about the limits of life and expand the spectrum of environments where it might exist beyond Earth. The discovery of life in deep-sea hydrothermal vents revolutionized our understanding of where organisms can survive. In these sunless depths, under crushing pressure and near-boiling temperatures, life not only persists, but thrives. Such conditions hint at the potential for similar ecosystems in the hidden oceans beneath the icy crusts of moons like Europa and Enceladus. Equally compelling are microbes inhabiting the driest deserts and coldest polar regions of Earth, demonstrating that life can endure scarcity of water and extreme temperatures. Their survival offers a tantalizing glimpse at the potential for microbial life on Mars or other seemingly barren worlds. Some extremophiles withstand intense radiation, suggesting that life might persist even on planets with thin atmospheres or exposed to harsh cosmic bombardment. Extremophiles also reveal that life can harness unconventional energy sources, such as hydrogen or methane, in place of sunlight. This discovery expands the range of potential habitats, from subsurface oceans to thick, chemically rich atmospheres, where life might find sustenance far from the warmth of a star. Studying these organisms informs scientists' search for extraterrestrial life, guiding the development of instruments and strategies to detect signs of life across the universe. The emergence of life itself remains one of the most profound mysteries in science, a phenomenon that continues to captivate researchers and thinkers alike. Viewed scientifically, life appears to arise from complex chemical interactions under precise conditions in the universe. With its staggering variety of stars, planets, and cosmic phenomena, offers countless arenas for these conditions to emerge. Observing the intricate processes that led to life on Earth inspires speculation about similar developments in distant worlds. Some theorists propose that the universe may possess inherent properties that favor the development of life. Known as the anthropic principle, this concept posits that the laws and constants of physics seem finely tuned to allow life to exist. While highly debated and far from implying any intentional design, this principle underscores the delicate interplay of forces and conditions that make life possible. Life, in its myriad forms and astonishing resilience, appears as a natural consequence of a universe capable of fostering complexity, a testament to the extraordinary potential embedded within the cosmic order. Ultimately, the question of whether the emergence of life is tied to a cosmic purpose stretches far beyond the grasp of empirical science, venturing into the realms of philosophy, theology, and human imagination. While modern science can meticulously examine the mechanisms, conditions, and processes that allow life to arise, assigning intention or purpose to these events is a profoundly subjective endeavor, shaped by individual beliefs and worldviews. Yet the sheer existence of life, fragile and intricate, sparks a sense of awe that has propelled humanity to explore the universe, driving our telescopes toward distant exoplanets, our probes to the far reaches of our solar system, and our imaginations to ponder humanity's role in the vast cosmic tapestry. Life as we recognize it requires a delicate orchestration of essential elements and precise environmental conditions. Water is paramount, often described as life's universal solvent. It serves as a medium where chemical reactions unfold, allowing organic molecules to interact, bond, and form ever more complex structures. Carbon, the backbone of life, exhibits a remarkable versatility, forming stable, intricate molecules capable of supporting the molecular complexity necessary for living systems. Energy, harvested from sunlight, geothermal heat, or chemical gradients, fuels metabolism, enabling cells to grow, repair, and reproduce. Equally crucial are nitrogen, phosphorus, and sulfur, each participating in the synthesis of amino acids, nucleic acids, and other critical biomolecules that compose the architecture of life. Temperature, often overlooked, exerts profound influence. Life cannot thrive in extremes of heat or cold, for proteins may denature, enzymes may falter, and cellular integrity may fail. Stability of the environment, shielding against harmful radiation, and permitting the slow accumulation of organic molecules is equally critical. Time, measured not in years but in eons, is the invisible architect of life. The assembly of complex molecules, the emergence of self-replicating systems, and the intricate dance of evolutionary processes unfold over millions or even billions of years. These conditions, governed by the immutable laws of chemistry and physics, set the stage for the astonishing emergence of living systems. Biogenesis, the concept that life arose from non-living matter, represents a cornerstone in the scientific quest to understand our origins. It explores how simple organic compounds, born of Earth's primordial chemistry, could gradually assemble into self-replicating organisms. Theories of abiogenesis propose that life might have sparked in a primordial ocean, a soup energized by lightning, ultraviolet radiation, or the venting heat of hydrothermal systems. Within this chaotic cradle, amino acids, the fundamental building blocks of proteins and other essential organic molecules, could have emerged. Researchers have also considered alternative birthplaces for life, mineral-rich clay surfaces, ice matrices, and other microenvironments that could have concentrated and protected nascent organic molecules, nurturing the first chemical networks capable of replication and metabolism. These studies inform our search for extraterrestrial life, offering clues to the types of environments where life might emerge elsewhere in the cosmos. Chemical evolution forms a crucial bridge between inert matter and the dynamic complexity of living systems. Simple molecules like amino acids and nucleotides, formed from inorganic precursors under the influence of energy sources such as ultraviolet radiation, lightning, and geothermal heat, gradually combined into polymers, proteins and nucleic acids that could perform essential biological functions. The advent of molecular self-organization allowed these compounds to assemble into primitive compartments, protocells or microspheres, where further reactions could unfold in a protected environment. Within these compartments, rudimentary metabolic cycles and information storage systems could develop, creating conditions ripe for life's first sparks. The eventual emergence of self-replicating molecules, likely RNA or chemically similar compounds, enabled the storage of genetic information alongside catalytic activity, laying the groundwork for increasingly complex biological systems. Biological evolution, unfolding over billions of years, drives the astounding diversity and complexity of life observed today. At the heart of this process lies natural selection. Organisms with traits better suited to their environments survive, reproduce, and transmit these advantages to their progeny. Genetic mutations and recombination provide the raw material for adaptation, occasionally yielding innovations that allow life to exploit new niches or withstand environmental challenges. Populations subjected to isolation or distinct pressures diverge through speciation, giving rise to new species and contributing to the rich tapestry of life. Evolution favors not only survival but specialization, leading to the emergence of organs, tissues, and biological systems finely tuned to ecological roles. The RNA world hypothesis offers a compelling glimpse into the earliest chapter of life on Earth. Before DNA and proteins dominated biological functions, RNA may have performed dual roles, storing genetic information and catalyzing chemical reactions. This duality made RNA a prime candidate for the first self-replicating molecules, capable of initiating the cascade that led to modern biochemistry. The discovery of ribozymes, RNA molecules that can catalyze chemical reactions, validates this hypothesis, demonstrating that RNA is not merely a passive informational molecule, but an active agent in chemistry, bridging the gap between simple molecules and the sophisticated machinery of life. Through these intertwined narratives of abiogenesis, chemical evolution, and biological evolution, humanity begins to piece together a story both intricate and profound. A story of molecules forming, organizing, and transforming over unimaginable stretches of time into the living world we inhabit today. It is a saga marked by chance and necessity, randomness and pattern, revealing not only the origins of life on Earth, but the tantalizing possibility that somewhere in the vast expanse of the cosmos, life, perhaps very different, perhaps eerily familiar, may have emerged through processes guided by the same fundamental principles that govern our existence. Additionally, researchers have uncovered RNA sequences capable of catalyzing their own replication, a monumental breakthrough in understanding the origins of self-sustaining life. These sequences provide a glimpse into a primordial world dominated by RNA, long before the emergence of the complex DNA-RNA protein systems that define life today. The RNA world hypothesis posits that RNA once carried both the instructions for life and the machinery to execute them, effectively acting as both blueprint and builder. Over time, DNA with its remarkable stability assumed the role of long-term information storage, while proteins, with their extraordinary versatility and catalytic efficiency, became the engines driving biochemical reactions. RNA, once the star player, transitioned to its modern role as a crucial intermediary, translating DNA's coded instructions into functional proteins. Investigating RNA's early role sheds light not only on the history of life on Earth, but also on the potential existence of life elsewhere in the cosmos. It implies that when scanning other planets or moons, scientists should consider the presence of RNA-based life or its precursors, expanding the criteria for what forms extraterrestrial life might take. Horizontal gene transfer presents another extraordinary phenomenon, one that radically reshapes our understanding of evolution. Unlike the conventional vertical inheritance of genes from parent to offspring, horizontal gene transfer allows organisms to acquire genetic material from entirely unrelated species. Microorganisms such as bacteria and archaea exploit this mechanism to rapidly adapt to environmental challenges. Genes can move via transformation, where cells absorb DNA from their surroundings, conjugation, involving direct DNA exchange between cells, and transduction, mediated by viruses carrying genetic material. The evolutionary implications are staggering. Traits that confer survival advantages, such as antibiotic resistance, can spread with unprecedented speed, allowing populations to adapt to new environments almost in real time. Horizontal gene transfer can even give rise to new species, contributing to the astonishing biodiversity observed on Earth. Beyond its practical effects, this process transforms the conceptual tree of life into a complex, interwoven network of genetic connections, illustrating a dynamic, ever-changing biosphere where genes flow not only downward through generations, but also sideways across species boundaries. Extremophiles, organisms thriving in environments once deemed uninhabitable, have rewritten the limits of biology. From scorching hydrothermal vents to frigid polar ice, from crushing oceanic pressures to highly acidic pools, extremophiles demonstrate life's astonishing resilience. Their existence has not only expanded the definition of habitable conditions on Earth, but also reshaped the search for extraterrestrial life. If life can endure Earth's most extreme niches, then it is plausible it might also survive on planets or moons with harsh, seemingly inhospitable conditions. This understanding prompts a reevaluation of habitable zones around stars and widens the scope of potentially life-bearing worlds in the universe. Extremophiles also illuminate Earth's own origins, hinting that life may have first emerged in extreme settings, such as deep-sea hydrothermal vents. The molecular mechanisms these organisms employ, specialized proteins, heat-stable enzymes, and protective biochemicals, demonstrate evolution's power to equip life with survival strategies in the harshest of conditions. Such adaptations suggest a universal tendency for life to arise wherever suitable chemical and physical conditions exist, hinting at the possibility that life is not an anomaly, but a recurring feature of the cosmos. Panspermia introduces a thrilling cosmic dimension to the story of life. This hypothesis posits that life, or its building blocks, may traverse the universe aboard asteroids, comets, or other celestial objects, seeding habitable environments far from their origins. Microorganisms or organic compounds could survive interstellar journeys, withstanding extreme radiation, vacuum, and temperature fluctuations until landing on planets or moons where conditions permit survival and growth. If panspermia holds true, life on Earth might share a common ancestry with life elsewhere, linking planets and moons across staggering cosmic distances. Evidence supporting this idea includes the remarkable durability of certain terrestrial organisms, such as bacteria and tardigrades, capable of enduring space-like extremes. While panspermia remains theoretical, it opens tantalizing avenues for astrobiology, suggesting that life may be more widespread in the universe than previously imagined, and that signs of familiar biochemistry could be detected on other worlds. The study of Earth's earliest life forms provides vital context for this exploration. Microorganisms that flourished billions of years ago under conditions hostile to modern life offer critical insights into how life might arise and persist elsewhere. Ancient extremophiles survived in acidic waters, oxygen-deprived environments, and regions of intense pressure and darkness, including ecosystems surrounding deep-sea hydrothermal vents. These discoveries suggest that similar niches could exist on other celestial bodies, capable of supporting life. For instance, subsurface oceans on icy moons like Europa or Enceladus may host microbial life forms comparable to those thriving in Earth's deepest oceans. Understanding these extreme survivors enriches our grasp of life's adaptability, demonstrating that the boundaries for habitability are far broader than previously thought, and providing a roadmap for where and how we might detect life beyond our planet. Furthermore, studying the chemical fingerprints left behind by ancient microbes opens a remarkable window into the earliest chapters of life, revealing subtle traces of biological activity that persist over billions of years. By meticulously analyzing these molecular clues, scientists gain the ability to recognize potential biosignatures on distant planets, identifying the faintest hints that life might exist beyond Earth. This scientific detective work informs every probe, telescope observation, and planetary mission, guiding researchers toward the specific atmospheric gases, mineral deposits, and surface patterns that could signal the presence of extraterrestrial organisms. Each discovery, each pattern observed in the chemical composition of alien worlds, brings humanity incrementally closer to answering one of the most profound questions ever posed. Are we alone in the cosmos, or is life a universal phenomenon that has emerged across the vast tapestry of the universe? The emergence of consciousness within this grand cosmic narrative introduces questions that are both deeply personal and astonishingly universal, challenging our understanding of existence and purpose. Humans, endowed with self-awareness, have long grappled with the idea that our capacity to perceive, reflect, and create meaning might be intertwined with a larger cosmic design. From a strictly scientific standpoint, consciousness appears to arise as an emergent property of extraordinarily complex information processing networks, such as the human brain. Over billions of years, as the universe evolved from a sea of fundamental particles into intricate galaxies, stars, planets, and ecosystems, it created the precise conditions necessary for conscious beings to exist, capable of observing, analyzing, and questioning their own existence. Some thinkers suggest that this is not mere coincidence, but a natural continuation of cosmic evolution, a universe that, through its own intricate unfolding, eventually produces entities capable of understanding itself. Yet this proposition remains a subject of intense debate, oscillating between interpretations of deliberate cosmic intent and the view that consciousness is simply a remarkable but random outcome of natural processes. The anthropic principle adds yet another layer of complexity, reminding us that the universe's physical constants and conditions are finely tuned in ways that allow observers like us to emerge. In other words, our very capacity to ponder questions of cosmic purpose is inseparable from the specific properties of the universe itself. This intertwining of observation and existence challenges the boundary between philosophy and science, placing humans at a peculiar vantage point where understanding our own consciousness may illuminate the universe's broader narrative, or perhaps reveal that the universe has no narrative at all. The continuing pursuit to comprehend both the cosmos and the nature of consciousness promises not only to expand our scientific knowledge, but also to deepen our sense of wonder and awe in the face of the vast, enigmatic universe we inhabit. The search for intelligent life beyond our planet is intimately connected to these contemplations, as humanity probes the far reaches of space in hopes of encountering civilizations that might offer new perspectives on existence itself. Advanced extraterrestrial societies, if they exist, may have achieved technological and philosophical milestones far beyond our comprehension, potentially unraveling aspects of reality that remain hidden to us. Their explorations could illuminate the very fabric of the universe, offering insights into the nature of consciousness, the origin of the cosmos, or even the existence of multiple universes. Perhaps these civilizations are engaged in large-scale projects that manipulate stellar energy, reshape planetary systems, or guide the evolution of entire galaxies. Observing or discovering such endeavors could reveal patterns or purposes in cosmic evolution that remain invisible from our current vantage point. The presence of a galactic community of intelligent species could redefine our understanding of humanity's role in the universe, suggesting a broader, interconnected narrative of conscious life. Yet it is equally conceivable that humanity occupies a pioneering position among the earliest intelligent species capable of contemplating such questions. In this scenario, our species might serve as the first observers, charting the cosmos with curiosity, ingenuity, and insight, laying the groundwork for future civilizations to expand upon. The trajectory of technological development across intelligent species can be interpreted as a natural extension of cosmic evolution itself. As life arises and intelligence emerges, the capacity to manipulate the environment, harness energy, and explore the far reaches of space becomes the next logical step in the universe's journey toward increasing complexity and self-awareness. Advanced civilizations, through innovation and exploration, become instruments through which the universe comes to know and shape itself, transforming from a vast, indifferent expanse into a dynamic arena of conscious observation, creation, and influence. In this sense, the rise of technology, the spread of intelligence, and the expansion of civilizations across space may represent the universe's own unfolding understanding of its existence, a narrative written in the stars and enacted through the minds and actions of conscious beings. However, it is crucial to recognize that the idea of a universal purpose remains deeply speculative. There is no definitive way to determine whether the cosmos operates according to an inherent goal or direction. The emergence and evolution of technology may simply be the natural outcome of physical and chemical laws unfolding over billions of years, rather than evidence of a predetermined cosmic plan. Yet, the fact that technology allows intelligent species to observe, study, and potentially influence the universe on scales that stretch across galaxies is extraordinary. It invites profound questions about the role of consciousness and intelligence in the broader tapestry of existence, and whether our technological achievements are threads in a larger cosmic narrative that we have only begun to perceive. Self-awareness itself stands as one of the universe's most remarkable phenomena, a mechanism through which the cosmos perceives and begins to understand itself. The rise of conscious beings like humans represents a turning point in cosmic evolution. Through our capacity for reflection, the universe gains the ability to contemplate its own origins, its structure, and the mysteries woven into its very fabric. Self-reflective consciousness allows us to explore fundamental questions about our existence, the nature of reality, and our position within the vast expanse of space and time. Beyond mere introspection, self-awareness fuels the development of complex theories and sophisticated technologies, enabling us to probe the universe's depths and even speculate about forms of consciousness that might exist beyond our planet. The significance of self-awareness extends far beyond individual cognition. It drives scientific inquiry, philosophical contemplation, and the search for meaning in a cosmos that may, at first glance, appear indifferent. From a cosmic perspective, consciousness may represent a natural outcome of increasing complexity. From the formation of subatomic particles to the assembly of atoms, molecules, and ultimately living organisms, the emergence of self-aware entities signals a higher level of organizational complexity. This progression raises profound questions. Is consciousness a fundamental property woven into the universe's fabric, or does it emerge only in complex systems capable of processing and integrating vast amounts of information? The existence of self-aware beings introduces the notion of cosmic responsibility. As intelligence grows and awareness of our influence expands, ethical considerations arise regarding our role in shaping the trajectory of life on Earth and potentially beyond. Self-awareness compels us to confront not only personal purpose, but also the collective purpose of intelligent species within a broader cosmic framework. Across the universe, intelligence manifests in myriad forms, each potentially contributing uniquely to the cosmic mosaic. From microscopic neural networks in Earth's simplest life forms to hypothetical superintelligent civilizations spanning entire galaxies, cognition and awareness may operate at countless scales, all interacting with and influencing the universe in ways we can barely imagine. Some intelligences might function as cosmic gardeners, nurturing life on barren worlds, while others may act as archivists of galactic history, preserving the accumulated knowledge of civilizations long extinct. Advanced intelligences might even manipulate the fabric of space-time itself, reshaping the universe in accordance with principles we are only beginning to comprehend. Interstellar collaboration among diverse intelligences could unlock discoveries beyond our current understanding, from the secrets of dark matter to harnessing the immense energies of black holes, and perhaps even transcending the physical limits that constrain present-day science. Through the combined observations, analyses, and interactions of countless conscious beings, the universe may slowly awaken to an understanding of itself, forming a vast, emergent cosmic mind. Problem-solving capacity has been critical in the evolution of intelligent life. As species encounter environmental challenges, individuals with superior abilities to solve complex problems are more likely to survive and pass on their traits. This adaptability allows organisms to acquire food, evade predators, navigate social hierarchies, and respond to shifting conditions. Across evolutionary history, species that developed enhanced problem-solving skills gained significant advantages. Early humans, for example, thrived by crafting tools, mastering fire, and developing language, abilities that enabled them to hunt efficiently, protect themselves from harsh conditions, and communicate intricate ideas. These skills are linked to the growth of brain size and complexity, which has allowed species like dolphins, elephants, and primates to tackle increasingly sophisticated challenges. In the context of extraterrestrial life, problem solving may be a hallmark of any civilization capable of technological advancement. The ability to innovate, adapt, and overcome obstacles could be essential for exploring their environments and venturing into the cosmos. Human capacity for abstract thought further enhances this pursuit. It allows us to consider realities far beyond immediate perception, to grapple with concepts like infinity, multiple dimensions, and the nature of time itself. Such abstract cognition is essential for constructing models of the universe, contemplating its origins, and hypothesizing its ultimate fate. By connecting patterns across scales, from quantum phenomena to galactic motion, we begin to glimpse the underlying principles that might govern existence. Yet, abstract thought also highlights the limits of human comprehension. The universe's vastness and complexity often defy complete understanding, reminding us that the quest for cosmic purpose is an endless journey, one that blends curiosity with awe. Collective intelligence magnifies these possibilities. Across the cosmos, patterns emerge, from the synchronized movements of celestial bodies to the interplay of galactic structures. On Earth, collective intelligence manifests through scientific collaboration and knowledge sharing, yielding breakthroughs such as the detection of gravitational waves and the exploration of distant planets. Extending this concept to the universe, we can envision a cosmic network of civilizations pooling knowledge, tackling mysteries that have eluded individual minds for millennia. Such collaboration could illuminate dark matter, trace the universe's origins, or uncover higher dimensions, accelerating comprehension at a scale unparalleled in human history. Artificial intelligence could further amplify this pursuit. Advanced AI systems may help analyze vast astronomical data sets, revealing patterns invisible to human observers, driving discoveries about the nature of reality and humanity's place within it. By extending cognition and problem-solving capacity through AI and collective intelligence, we take steps toward a universe capable of self-reflection, where each conscious entity contributes to the gradual awakening of cosmic awareness, bridging the gap between mere existence and profound understanding. Furthermore, artificial intelligence holds the potential to revolutionize humanity's quest to understand whether we are alone in the cosmos. By meticulously analyzing the immense complexity of signals received from distant stars and galaxies, AI can detect subtle patterns that might otherwise elude human observation, potentially identifying faint indications of extraterrestrial civilizations. If such civilizations were to exist and we managed to establish contact, AI could become an indispensable intermediary, deciphering alien communications and bridging the gaps in understanding across entirely unfamiliar cognitive frameworks. As artificial intelligence grows increasingly sophisticated, it might even offer unprecedented insights into the nature of consciousness, intelligence, and the fundamental workings of the universe itself, prompting us to reevaluate whether these qualities are intrinsic to the cosmos, aligning with philosophical theories such as panpsychism or cosmic consciousness. In practical terms, the capacity of intelligent life to manipulate and transform its environment plays a crucial role in its cosmic significance. Species that evolve advanced cognitive functions gain the ability to shape their surroundings, a capability that can ripple outward with profound consequences for their planets and beyond. This environmental mastery often coincides with technological development, granting civilizations the ability to harness energy, construct sophisticated tools, and extend their reach into space. Such exploration may eventually lead to the colonization of distant worlds and the detection of other intelligent life forms across the galaxy, reinforcing a feedback loop of discovery, innovation, and survival. The ability to manipulate one's environment also directly affects the long-term prospects of a civilization. Species capable of mitigating planetary challenges such as climate shifts, dwindling resources, or asteroid impacts can increase their likelihood of enduring across cosmic timescales. potentially influencing regions far beyond their homeworlds. Yet with such capability comes immense responsibility. Civilizations must balance progress with sustainability to avoid self-destruction or ecological collapse on both planetary and interstellar scales. The true cosmic significance of intelligent life ultimately hinges on how judiciously these powers are exercised, and whether advanced species can navigate the delicate interplay between innovation and preservation. The search for extraterrestrial intelligence, known as SETI, embodies humanity's desire to locate meaning and connection on a universal scale. It is far more than a scientific pursuit. It is a profound inquiry into our own place in the cosmos. By scanning for evidence of advanced civilizations, we confront the question of whether consciousness is a rare anomaly or a natural consequence of cosmic evolution. Techniques employed by SETI range from traditional radio astronomy, which listens for narrowband signals potentially indicative of artificial transmissions, to optical methods that search for fleeting, high-intensity laser pulses that could serve as interstellar communication or propulsion mechanisms. Modern searches have expanded to include technosignatures, such as the heat emissions from hypothetical megastructures or the chemical traces of industrial activity in exoplanetary atmospheres, and even signs of astroengineering, where advanced civilizations might deliberately reshape entire star systems. Each of these approaches, even in the absence of direct discovery, yields invaluable knowledge about the universe, from stellar dynamics to planetary composition, and challenges us to rethink the parameters of intelligence and technological progress. Integral to these efforts is the Drake equation, formulated in 1961 by astronomer Frank Drake, which provides a structured way to estimate the number of technologically communicative civilizations within our galaxy. By considering factors such as the rate of star formation, the proportion of stars with planetary systems, the number of habitable planets per star, the probability of life developing intelligence, and the lifespan of advanced civilizations, the equation frames the cosmic question in a tangible, investigative context. While it cannot yield definitive numbers, it functions as a compass, guiding research into exoplanets, biosignatures, and the conditions necessary for life to arise, simultaneously expanding the disciplines of astronomy, biology, and astrobiology. The Drake equation emphasizes that our exploration is not only about finding others, but about refining our understanding of our own cosmic circumstances. Yet, the apparent absence of detectable extraterrestrial civilizations presents a paradox. The Fermi paradox highlights the dissonance between the sheer scale of the universe, with its billions of galaxies and myriad potentially habitable worlds, and the lack of evidence for other intelligent life. This discrepancy forces contemplation of unsettling possibilities. Intelligent life might be extraordinarily rare, making Earth an anomaly, or advanced civilizations might habitually self-destruct before achieving interstellar communication, implying a grim universal trend. Alternatively, it may indicate limitations in our detection methods or fundamental misunderstandings about how intelligent species evolve and behave. The paradox challenges humanity to confront the fragility of intelligence, the responsibilities inherent in technological advancement, and the profound implications of our search for meaning in a vast, largely silent cosmos. Artificial intelligence, by amplifying human analytical and cognitive capabilities, could play a decisive role in addressing these questions, helping to sift through vast data sets, model complex evolutionary scenarios, and even simulate alternative forms of consciousness. In doing so, it would not only augment our capacity to detect life elsewhere, but also deepen our philosophical understanding of intelligence, the responsibilities of advanced civilizations, and the ultimate trajectory of life in the universe. As humanity stands on the threshold of these cosmic inquiries, AI becomes more than a tool. It becomes a lens through which we might glimpse the deeper structure of existence, our potential purpose, and the fate of intelligent life across the stars. Moreover, the paradox challenges the very foundations of our understanding, forcing us to confront the possibility that our knowledge and perception may be inherently limited. Are we blind to the signs of alien intelligence, unable to recognize forms of life that operate on principles unlike our own? Or are we simply directing our gaze to the wrong corners of the cosmos? These questions push the human mind to expand beyond familiar boundaries, demanding a radical rethinking of what life and intelligence could look like in a universe so vast and varied. They ignite a drive to explore not just the known, but the potential, prompting scientific inquiry that stretches imagination to its outermost limits. Radio telescopes stand at the forefront of this search, acting as our ears across the vastness of space, known in the scientific community as instruments for the search for extraterrestrial intelligence, or SETI. These enormous dish-shaped structures are capable of detecting and capturing faint radio signals traveling across light years. Their design allows them to tune into frequencies that might plausibly carry communications from civilizations far more advanced than our own. Among these frequencies, the hydrogen line, occurring at 1,420 megahertz, holds particular significance. Hydrogen is the most abundant element in the universe, and scientists theorize that any intelligent civilization aware of the cosmos would recognize its importance, potentially using it as a cosmic beacon for communication. These radio telescopes scan the heavens with patient persistence, sifting through immense quantities of data in search of patterns, repetitions, or anomalies that could betray the presence of intelligent origin. Their utility lies not only in their sensitivity, but in the very nature of radio waves, which can traverse astronomical distances without significant degradation, making them an ideal medium for interstellar messaging. Among the largest and most capable of these instruments were the Arecibo Observatory in Puerto Rico, operational until 2020, and the 500-meter aperture spherical telescope in China, a modern marvel continuing to peer deep into the galaxy. Together, they probe the cosmos, ever vigilant for a signal that could redefine humanity's understanding of its place in the universe. The search for techno-signatures, indications of technology developed by alien civilizations, carries profound implications. Discovering even a single techno-signature would suggest that intelligent life is not a cosmic fluke, but a recurring outcome of the evolutionary processes that shape planets and stars. It would hint that the universe possesses conditions favorable to life, conditions that have repeatedly given rise to conscious beings capable of creating, innovating, and exploring. Such a discovery would compel us to reconsider the very nature of cosmic laws, perhaps revealing that physics and chemistry are structured in ways that allow not only matter to exist, but intelligence to emerge and thrive. Moreover, detecting techno-signatures could illuminate the longevity and resilience of technological civilizations. If we observe evidence of long-surviving extraterrestrial societies, it may suggest that intelligence can endure existential threats, adapt, and flourish over millennia. This insight could imply a broader cosmic narrative, one in which life and intelligence are not merely transient phenomena, but part of a larger tapestry, stretching across galaxies, linking civilizations, and weaving an intricate network of knowledge, exploration, and perhaps interstellar collaboration. Yet the absence of detectable techno-signatures does not preclude this cosmic potential. The universe may harbor life forms or modes of intelligence beyond our capacity to perceive or understand, reminding us of the humility and patience required in the quest to comprehend the cosmos. Exoplanet atmospheres provide another crucial dimension in the search for life beyond Earth. These gaseous layers encasing distant worlds carry the chemical fingerprints of their planet's potential habitability. Scientists examine them closely for biosignature gases, molecules that on Earth arise primarily from biological activity. Oxygen, abundant in our atmosphere thanks to photosynthetic organisms, and methane, often produced by microbial life, are prime examples. Detecting these substances elsewhere could signal active biological processes on worlds far beyond our solar system. The composition of an exoplanet's atmosphere also reveals critical information about its climate, weather patterns, and surface conditions, helping researchers assess whether liquid water, the fundamental prerequisite for life as we know it, could exist there. In tracing these subtle cosmic clues, from faint radio signals to the chemical signatures in alien skies, humanity engages in a profound exploration of its own place in the universe. Each discovery or absence thereof expands the scope of our understanding, revealing not just what is, but what could be. It is a journey that merges scientific rigor with boundless imagination, challenging our assumptions, reshaping our philosophies, and stretching the limits of what we dare to conceive about life, intelligence, and the vast unfolding mystery of the cosmos. Additionally, the subtle characteristics of a planet's atmosphere can serve as silent clues to its deeper nature. The presence of a magnetic field, for example, is often inferred from the way an atmosphere behaves. Such a field acts as an invisible shield, protecting the planet from harmful cosmic radiation and solar winds while preventing the gradual escape of gases into space. In this sense, a magnetic field is not merely a physical phenomenon, but a guardian of potential life. Beyond natural indicators, the fingerprints of advanced civilizations might also linger within the air. Certain chemical compounds, industrial pollutants, synthetic molecules, or other unnatural signatures could betray the workings of technological societies long before any physical visitation occurs. Detecting such traces with current telescopes is an extraordinary challenge, yet future innovations in atmospheric spectroscopy promise the tantalizing possibility of recognizing the presence of extraterrestrial intelligence across the light years. The concept of a galactic habitable zone further guides the search for life among the stars. This zone is a sprawling region within the Milky Way where conditions are thought to be particularly favorable for the emergence and survival of complex organisms. It acts as a cosmic sieve, narrowing the vast expanse of our galaxy to areas where life is more likely to thrive. Within this zone, stars occupy a Goldilocks position. They are neither dangerously close to the volatile center of the galaxy, where radiation and frequent supernovae could sterilize planets, nor so far out that the scarcity of heavy elements hinders the formation of rocky worlds or complex chemistry. This delicate balance allows for the accumulation of the essential building blocks of life while providing relative protection from catastrophic events. The galactic habitable zone forms a ring roughly 20,000 to 30,000 light-years from the galactic core, a region in which our own solar system comfortably resides. By focusing observational efforts on stars within this zone, scientists increase the likelihood of discovering habitable worlds or intercepting signals from advanced civilizations. Interstellar communication represents a profound extension of humanity's innate curiosity, a bridge from our small blue planet to the cosmic expanse. Through deliberate acts, such as the Arecibo message or the golden records aboard the Voyager spacecraft, we reach out into the void, conveying our presence, knowledge, and aspirations. These messages reflect a deep yearning for connection and recognition, an expression of hope that we are not alone, and that somewhere across the galaxy, others may ponder the same questions of existence, purpose, and understanding. To receive a response would be transformative, offering insights into alien perspectives on physics, philosophy, and perhaps even spirituality. The act of sending messages is itself a catalyst for human advancement, pushing technological boundaries, refining scientific methods, and expanding our comprehension of intelligence, communication, and the cosmos. The Great Filter Hypothesis casts a sobering shadow over the search for extraterrestrial life. It posits that throughout the evolution of life, from simple organisms to advanced civilizations, there exist critical barriers so formidable that most species fail to overcome them. Considering the immensity of the universe, with billions of potentially habitable planets, the apparent scarcity of advanced civilizations is striking. The Great Filter suggests that survival and development are extraordinarily difficult, and that most life never progresses past certain thresholds. Its implications are profound. If humanity has already passed the Great Filter, we may occupy a unique and pivotal role in the cosmos, perhaps as one of the rare civilizations to have achieved advanced intelligence. Conversely, if the filter lies ahead, the challenges that await could be monumental, framing the choices we make today as matters of cosmic consequence. Humanity's actions, exploration, and innovation may determine whether intelligence can continue to flourish across the stars or whether it is doomed to remain a fleeting phenomenon. Time, the invisible thread woven through the universe, plays a crucial role in this cosmic narrative. It is not merely a measure or a backdrop, but an active force shaping the evolution of matter, energy, and complexity. Stars are born and die, galaxies collide and spin, and the universe grows in intricacy. all under the inexorable passage of time. From the simple uniformity of the early cosmos to the elaborate structures we now observe, the universe's story is written in the language of temporal progression. Some theorists speculate that time itself might function as a cosmic processor, driving the accumulation of information and the emergence of complexity. Others consider the forward march of the temporal arrow as guiding the universe towards some ultimate state, perhaps one of maximum entropy or a form of cosmic equilibrium, yet beyond our comprehension. These reflections suggest that understanding time is inseparable from understanding the universe's potential purpose, revealing a cosmos that is at once vast, ordered, and full of mystery, where every passing moment contributes to a story billions of years in the making. Ultimately, the intricate relationship between time and the universe's overarching purpose remains one of the most profound enigmas in modern cosmology. As humanity continues to peer into the vastness of the cosmos, pushing the boundaries of observation and theory, we may gradually uncover subtle threads revealing how time shapes the grand architecture of the universe. Each discovery brings with it tantalizing hints about the universe's ultimate destiny, and perhaps even the underlying rationale behind its existence. The arrow of time stands as a central pillar in this exploration, embodying the unyielding, one-way flow of events from the distant past toward an ever-unfolding future. This inherent irreversibility is woven into the very fabric of space-time, orchestrating the universe's evolution from the first infinitesimal moments after the Big Bang to the complex structures and phenomena we observe today, and extending far beyond into the incomprehensible stretches of future cosmic history. In cosmic terms, the arrow of time manifests in multiple, intertwined ways. The universe's relentless expansion is perhaps the most striking example, as the fabric of space itself continues to stretch, pushing galaxies ever farther apart. This expansion is not a mere oscillation or a repeat of a previous contraction. It is a continuous, unidirectional process that defines the large-scale architecture and evolution of the cosmos. Simultaneously, the arrow of time is observable in the formation and development of cosmic structures. Gravity, the unseen sculptor, draws matter together, creating stars, galaxies, and colossal clusters of galaxies. These formations increase the complexity and organization of matter, giving rise to the intricate tapestry of the observable universe. Stars, as luminous engines of change, undergo life cycles in which they are born, shine for millions or billions of years, and ultimately die, irrevocably altering the chemical composition of their surroundings by forging heavier elements that seed future generations of celestial bodies. Even more profoundly, the arrow of time is intimately connected to the concept of entropy, a measure of disorder or randomness within a system. According to the second law of thermodynamics, the total entropy of an isolated system can only increase over time. This inexorable trend underpins countless cosmic processes, from the cooling and spreading of energy in the early universe to scenarios envisaging its distant future, such as heat death. Entropy acts as a cosmic metronome, guiding the progression of events and revealing why time itself appears to flow in one direction. The principle explains the irreversibility of processes we take for granted, from the blending of hot and cold water to the irreversible transformation of matter within stars and galaxies. The gradual rise of entropy also offers intriguing, if sobering, insights into the universe's potential purpose. Some theorists propose that the ultimate cosmic destiny may be a state of maximum entropy, in which energy is evenly dispersed and no further work or change is possible, a scenario often referred to as the universe's heat death. Such a future prompts profound questions about the meaning of existence itself. Yet entropy does not entirely preclude the formation of order. Localized decreases in entropy can arise within larger systems that are increasing in overall disorder, allowing for the emergence of complex structures such as galaxies, planetary systems, and even life itself. These pockets of order amidst chaos add a rich layer of nuance to our understanding of cosmic evolution and hint at the universe's capacity to generate meaning through structure and organization, even in the face of entropy's relentless march. Cosmic expansion continues to shape the temporal narrative of the universe, propelling space outward in a process first observed by Edwin Hubble in the 1920s. Galaxies move away from one another at accelerating speeds, a phenomenon that cools the universe and reduces its overall density over time. These conditions have delineated distinct cosmic eras, from the searing, densely packed early universe to the formation of fundamental particles, atoms, stars, and galaxies. The current rate of expansion holds profound implications for the cosmos's ultimate fate. Should expansion persist and accelerate as current observations suggest, the universe may face a big freeze, a desolate state in which stars burn out, galaxies drift into isolation, and matter becomes increasingly dispersed. The pace of expansion also limits what we can observe as distant galaxies recede faster than their light can reach us, effectively vanishing from view. Understanding cosmic expansion is therefore essential for decoding the universe's history, composition, and potential end. Some cosmological models, particularly cyclic theories, propose a radically different perspective, suggesting the universe undergoes endless cycles of expansion and contraction rather than possessing a singular beginning or conclusion. In these frameworks, existence itself becomes the primary reality, with each cycle offering the opportunity for new configurations of matter, energy, and physical laws. Complexity in life might arise in some cycles while other epochs remain barren, and certain fundamental patterns or information could persist from one cycle to the next, hinting at a form of cosmic evolution extending across unimaginable timescales. Such models invite a profound rethinking of purpose, presenting it not as a fixed goal but as an ongoing process of creation, transformation, and renewal. The concept of cosmic epochs provides additional context for understanding the universe's intricate timeline. Each epoch marks a significant transition, offering a window into how the cosmos evolved from its earliest, intensely hot and dense state to the sprawling, structured universe we inhabit today. From the formation of the first atoms to the birth of stars and galaxies and the subsequent acceleration of cosmic expansion, these epochs act as milestones that frame the sequence of astrophysical events. They reveal the interdependence of cosmic phenomena, where the outcome of one epoch sets the stage for the next, weaving a continuous narrative of transformation across billions of years. Finally, the notion of heat death casts a stark, contemplative shadow over the universe's ultimate trajectory. As entropy steadily increases, the cosmos may approach a state of uniformity where energy is evenly distributed and all processes cease. Stars will exhaust their fuel, black holes will evaporate, and even the tiniest particles may decay. This eventual uniformity raises fundamental questions about purpose and significance. While some perceive this outcome as an ultimate futility, others argue that the existence of life and complex structures in the present moment grants the universe intrinsic meaning, however fleeting. The mere capacity to observe, reflect, and seek understanding may itself be a manifestation of purpose, a transient but profound testament to the richness of cosmic evolution. Time, entropy, expansion, cyclicity, and cosmic epochs intertwine to create a narrative of relentless progression, unfolding complexity, and the delicate balance between order and chaos. Within this vast, ever-changing framework, the universe continues to evolve, persistently revealing hints of its past, its present, and its possible futures, challenging us to consider our place within its infinite expanse. Moreover, our present understanding of physics, despite centuries of inquiry and experimentation, may be only a fragment of a far grander picture. As we probe deeper into the cosmos, it becomes increasingly plausible that future discoveries could unveil mechanisms that prevent heat death or introduce entirely new frameworks for cosmic evolution, mechanisms so profound that they would redefine everything we believe about the fate of the universe. The relentless quest to decipher these mysteries, to uncover the fundamental principles that govern existence itself, continues to propel both scientific exploration and philosophical reflection, compelling humanity to confront questions as ancient as thought itself. Why are we here, and what is the ultimate destiny of all that exists? Time dilation and relativity fundamentally reshape our perception of cosmic timescales, revealing that time is not a fixed constant, but a malleable dimension, intricately influenced by gravity and motion. According to Einstein's theory of relativity, time does not flow uniformly across the universe. Instead, it bends and stretches depending on an object's velocity or its proximity to massive bodies. In regions of extreme gravity, such as near black holes, these effects become starkly pronounced. Time slows dramatically, meaning events occurring close to the edge of a black hole's event horizon may seem to take billions of years when observed from Earth, while mere moments elapse for a hypothetical observer nearby. Relativity also reshapes our view of the early universe. The light reaching us from distant galaxies has journeyed across billions of years, stretched and distorted by the very expansion of space itself, a phenomenon known as cosmological redshift. This stretching provides an invaluable window into the universe's history, allowing scientists to look back almost to the very moment of the Big Bang. These relativistic effects challenge our intuitive notions of time and space, revealing a cosmos far more intricate and interconnected than classical physics once suggested, where time and space form a single dynamic tapestry that evolves in concert with the matter and energy within it. Eternal inflation offers an even more staggering perspective. It proposes that our universe is merely one bubble within a vast, ever-expanding cosmic foam, a universe among potentially infinite others, each with its own distinct laws of physics and structures. Inflation, the rapid expansion that occurred in our universe's earliest moments, may not have ended at all, but could continue perpetually, generating new bubble universes without cessation. This concept dismantles traditional notions of a singular cosmic purpose. If universes are continuously forming, each with unique properties, then assigning a single overarching purpose to existence becomes problematic. Meaning may not reside in the multiverse as a whole, but rather emerge locally within each universe, or even be created by the conscious beings that inhabit them. The timeline of the cosmos, once thought linear, now expands into a vast, possibly infinite continuum where new universes are perpetually born. Our universe, with its 13.8 billion year history, becomes just one fleeting thread in an immense interwoven cosmic tapestry, stretching beyond comprehension, suggesting that the story of our cosmos is one narrative among an endless multiplicity of cosmic tales unfolding simultaneously. Cosmic microwave background radiation provides a remarkable tool for understanding the early universe and its evolution. This faint, omnipresent glow, the afterglow of the Big Bang, offers a snapshot of the cosmos when it was a mere 380,000 years old. By analyzing subtle variations in temperature and polarization, scientists extract vital information about the universe's composition, structure, and the seeds from which galaxies, stars, and planets ultimately formed. These minute fluctuations, only 1 part in 100,000, represent the primordial structures that would give rise to the intricate cosmic web we observe today. Furthermore, the cosmic microwave background provides compelling evidence supporting the inflationary model, demonstrating a period of extraordinary rapid expansion in the universe's infancy, explaining both the radiation's uniformity and the large-scale flatness of space. While this radiation illuminates the how of the universe, it leaves the question of purpose untouched. Science can describe mechanisms, chart histories, and predict futures, but it cannot dictate meaning, which remains the domain of philosophy, consciousness, and subjective reflection. The concept of information offers a profound lens through which to view the universe's potential purpose. At its essence, information represents patterns, structures, and the relationships binding the elements of reality. Viewed cosmically, the universe can be considered a vast repository and processor of information. Some theorists posit that information is the universe's fundamental substrate, suggesting that the cosmos itself operates as a colossal, self-organizing computational system. Physical laws in this context are not mere descriptions, but encoded data shaping the behavior of the universe. From this perspective, one might argue that the universe exists to generate, process, and refine information, with complexity itself as the ultimate output. The formation of galaxies, the emergence of life, and the evolution of intelligence can be seen as progressively sophisticated mechanisms for information processing. Conscious beings, particularly humans, capable of interpreting, manipulating, and reflecting upon information, may occupy a central role in the universe's ongoing computational narrative, raising profound questions about whether the development of intelligence is an intrinsic cosmic function. Complexity drives the evolution of the universe from its simplest origins to the intricate structures we observe today. Following the Big Bang, the cosmos expanded and cooled, allowing fundamental particles to coalesce into atoms, then molecules, and eventually stars, planets, and life-bearing systems. This evolutionary trajectory of complexity is not merely quantitative, it is qualitative, manifesting in emergent behaviors and novel properties. When the first stars ignited, nuclear fusion forged heavier elements, setting the stage for ever more sophisticated structures, from planetary systems to living organisms. Some theorists suggest that this relentless increase in complexity reflects a deeper tendency within the cosmos, an inherent drive toward organization and elaboration, a principle some refer to as cosmic evolutionary synthesis. This perspective posits that the universe is not chaotic or random, but is inclined over time to produce increasingly intricate, interdependent systems, each level of complexity building upon the last, culminating in phenomena capable of consciousness, reflection, and perhaps even self-awareness within the vast cosmic panorama. In this grand tableau, the universe emerges not as a static arena, but as a dynamic, information-rich, ever-evolving system. Its timelines are vast and entangled, its structures increasingly sophisticated, and its underlying mechanisms subtle yet profoundly interconnected. From the bending of time near black holes to the emergence of intelligence as a cosmic participant, from the faint whispers of cosmic microwave background radiation to the boundless proliferation of bubble universes in eternal inflation, the cosmos presents a narrative of both staggering scale and intricate detail. Every discovery, every insight reveals another layer of the universe's complexity, and with each revelation, humanity inches closer to understanding not only the how of existence, but perhaps glimpses of its ultimate purpose within an infinite, ever-expanding multiverse. However, it is crucial to recognize that this concept remains highly speculative and has yet to achieve universal acceptance within the scientific community. The idea that complexity might play a defining role in cosmic evolution opens profound questions about the very nature of our universe and the place of life within it. As humanity continues its exploration, attempting to unravel the intricate mechanisms underlying cosmic phenomena, new insights may emerge, shedding light on the fundamental workings of reality itself, and perhaps even hinting at the hidden principles orchestrating the vast universe around us. The rise of complex systems within the cosmos challenges us to rethink assumptions about purpose and order. When we observe the universe, a pattern of increasing complexity becomes evident, beginning with the formation of the most basic atomic structures and extending to the birth of stars, the formation of galaxies, and ultimately the emergence of life in all its diversity. This journey from simplicity to ever greater complexity unfolds through natural processes guided meticulously by the immutable laws of physics. Despite arising spontaneously, these systems exhibit remarkable levels of organization and efficiency. Consider, for example, the intricate interdependencies of ecosystems, or the highly precise biochemical interactions occurring within living cells. These self-organizing systems demonstrate an elegance and sophistication that can appear purposeful, even without the intervention of a conscious designer. Certain scientists and philosophers have argued that this intrinsic tendency toward complexity and organized structure suggests an inherent drive within the universe itself. They propose that the cosmos may possess a natural propensity to create progressively intricate structures and relationships, implying a subtle form of directionality in its unfolding. This idea forces us to confront the question of whether apparent purpose can arise from beginnings that were entirely devoid of intent. Nevertheless, it is essential to remember that the mere appearance of purpose does not equate to conscious intent. The development of complex systems can be thoroughly explained through processes such as natural selection, self-organization, and the governing laws of physics, without the necessity of invoking a universal purpose. This ongoing debate compels us to reflect on the nature of existence and humanity's role in the cosmos. Self-organizing systems are central to cosmic evolution, acting as engines driving the formation and development of increasingly complex structures throughout the universe. These systems emerge spontaneously from simpler constituents, generating patterns, order, and organization without any external guidance. In the context of cosmic evolution, understanding self-organization is fundamental to comprehending how the universe transformed from its nearly uniform state following the Big Bang into the astonishingly diverse and structured cosmos we observe today. On the grandest scales, self-organization is manifest in the cosmic web, a vast, interconnected lattice of dark matter filaments, galaxy clusters, and voids, all arising naturally from minuscule density fluctuations in the early universe and evolving over billions of years into the intricate cosmic architecture visible today. On smaller scales, self-organization drives the formation of stars and planetary systems. Immense clouds of gas and dust collapse under their own gravitational pull, forming dense cores that ignite into stars, while the residual material gradually coalesces into planets, moons, and asteroids, building solar systems through the complex interplay of accretion and gravity. Even within biology, self-organization plays a vital role. The spontaneous formation and interaction of complex organic molecules, which eventually leads to self-replicating systems, exemplifies the universality of these principles, bridging cosmic and microscopic scales. Emergence is another key concept in understanding the universe's complex architecture. Emergence describes how intricate patterns and behaviors arise from the interactions of simpler elements, producing properties that cannot be anticipated merely by analyzing individual components. Applied to cosmic evolution, emergence explains how the vast and highly structured cosmic web evolved from the relatively uniform conditions following the Big Bang. Galaxies, stars, and planetary systems all exemplify emergent phenomena. The collective behavior of countless particles gives rise to organized structures with properties and behaviors that transcend their basic constituents. Emergence also has profound implications for the question of purpose and meaning. As complexity grows, new capabilities arise. Life on Earth, for instance, introduces consciousness and the capacity for observation and exploration, allowing the universe to contemplate itself. This invites speculation about whether similar emergent properties might manifest on cosmic scales, producing complexities and perhaps even forms of awareness beyond current human comprehension. While emergence does not mandate a predetermined cosmic purpose, it does highlight the universe's potential to generate increasingly sophisticated structures and phenomena, encouraging us to imagine that complexity may continue to unfold in ways not yet realized. Entropy, a foundational concept in physics, underpins the creation and eventual decay of complex systems across all scales. At its essence, entropy measures the tendency of energy to disperse and matter to move toward disorder over time. This principle governs the life cycles of stars and galaxies, the evolution of planets, and even the development and decline of living systems and human societies. Yet entropy interacts with complexity in fascinating ways. While the universe's overall entropy inexorably rises, localized decreases in entropy allow organized structures to form temporarily, creating pockets of order within a broader trend of chaos. The birth of stars and planetary systems illustrates this phenomenon. Matter condenses and organizes under gravity, producing structured, functional systems despite the universe's overall drift toward disorder. Over time, however, entropy prevails. Stars exhaust their nuclear fuel and collapse, planets cool and stabilize, and even galaxy clusters will eventually succumb to the relentless march of disorder. This tension between entropy and order is especially evident in living systems, which maintain highly organized states by continually consuming energy, only to eventually succumb to entropy's unyielding influence. Information theory provides additional insights into the quest to understand cosmic purpose. This mathematical framework, concerned with the quantification, storage, and transmission of information, offers profound implications for interpreting the universe and its potential meaning. Entropy, in the context of information theory, measures disorder or randomness, paralleling its thermodynamic definition. Viewed cosmically, this suggests a trend toward increasing complexity and information content over time, from the early universe's relative simplicity to the present-day intricacy of galaxies, planetary systems, and life itself. Information preservation is another concept with deep cosmic significance. Some physicists propose that information cannot be truly destroyed, even during extreme events like black holes. This idea hints at an underlying continuity and significance in the universe's structures. potentially pointing toward a more profound pattern or purpose woven into the very fabric of existence. The universe, in its immense vastness and complexity, may thus be both a playground and a laboratory, where natural laws, self-organization, emergence, entropy, and information interact to produce the astonishing tapestry of reality, guiding the relentless unfolding of cosmic history toward patterns of complexity that continue to inspire wonder and inquiry. Furthermore, information theory offers a profound framework for grasping how extraordinarily complex systems, including life itself, can emerge from deceptively simple building blocks. It invites us to reconsider the development of consciousness and intelligence not as random accidents, but as potentially inherent tendencies of the cosmos, woven into the very fabric of existence. From this vantage point, the universe may appear in some sense purposeful, a grand experiment in complexity and self-organization, rather than a chaotic collection of chance events. Fractal patterns exemplify this hidden order, manifesting throughout nature and across the vast reaches of the cosmos. These self-similar structures repeating across multiple scales are evident everywhere, in the intricate branching of trees, the delicate symmetry of snowflakes, the winding curves of rivers, and even the sprawling clusters of galaxies across the universe. Fractals emerge not merely as patterns, but as efficient solutions to the challenges of complex systems. The branching architecture of human lungs, for instance, maximizes the surface area available for gas exchange while minimizing the space required, a delicate balance of efficiency and design. Similarly, the fractal intricacy of coastlines facilitates the most effective interaction between land and sea. On a cosmic scale, fractal patterns emerge in the large-scale structure of the universe itself. Galaxies congregate into clusters, which in turn form superclusters and interconnected filaments, creating a vast cosmic web. Remarkably, this structure mirrors, in an almost uncanny way, the networked neurons of the human brain or the intertwined mycelial networks of fungi. This recurring pattern across such disparate scales hints at a fundamental principle of organization, suggesting that the same rules that shape tiny biological systems might also govern the formation of entire galaxies. The ubiquity of fractals in nature and the cosmos reveals a profound link between mathematics and reality, demonstrating how simple, elegant rules can generate immense complexity. It hints that underlying principles orchestrate the growth and formation of systems from the microscopic to the cosmic. Recognizing these patterns reshapes our understanding of the universe, suggesting a universe where structure, order, and efficiency are deeply embedded, and positioning humanity as observers and participants within this grand, interconnected design. The holographic universe theory expands this perspective even further, proposing that the entirety of the cosmos may function as a three-dimensional projection of information encoded on a two-dimensional boundary. In essence, our physical reality could be a vast, dynamic hologram where depth, space, and matter emerge from underlying informational patterns. In this framework, information is not secondary or abstract, it is foundational. The universe, much like a cosmic computer, processes, stores, and manipulates information, encoding every event from galactic collisions to the fleeting thoughts in our minds into an immense, interconnected informational tapestry. This view aligns intriguingly with contemporary discoveries in quantum physics and information theory, hinting at a deep interrelation between the nature of reality and information itself. Consciousness, then, may not merely be a byproduct of matter, but a vital participant in the universe's ongoing information processing. If reality is fundamentally informational, our conscious experience could be integral to the unfolding of the cosmos, participating in the encoding, interpretation, and transformation of the universe's data. This perspective opens doors to profound questions about the nature of mind, matter, and the possible purpose embedded in the cosmic order. At the quantum level, information becomes even more fundamental. The universe operates according to quantum mechanics, where every particle and system carries information within its quantum states. This quantum information dictates how matter and energy interact, combine, and evolve, forming the basis of atoms, molecules, stars, and galaxies. Quantum phenomena such as superposition and entanglement, which seem paradoxical from a classical perspective, are essential for understanding how these fundamental building blocks behave. Some theorists even propose that The universe itself is a colossal quantum computer with quantum bits or qubits, continuously computing and evolving across space-time. From this viewpoint, the very fabric of the universe is a dynamic flow of quantum information shaping the cosmos from the ground up. Every structure, every pattern, every event emerges from this relentless processing, revealing a cosmos where information is not just a property of systems, but their essence. The evolution of stars, the formation of galaxies, and even the rise of consciousness could be understood as expressions of the universe computing itself, a continuous unfolding of complexity from the quantum substratum to the cosmic scale. In this light, our understanding of existence shifts dramatically. The universe is not merely a backdrop for life and consciousness. It is an active, informational entity where every quantum fluctuation, every pattern of fractal growth, and every human thought participates in the ongoing computation of reality. This perspective suggests that the cosmos is simultaneously a theater of matter, a canvas of patterns, and a living information processing system, inviting us to reconsider our place, our purpose, and our role in the grand unfolding of existence. Furthermore, the concept of quantum information has revolutionized our understanding of the cosmos, inspiring some of the most daring and imaginative theories in modern physics. Among these is the notion that black holes are not merely cosmic vacuum cleaners, but intricate repositories of information. This leads directly to the holographic principle, a mind-bending idea suggesting that all the information contained within our vast three-dimensional universe might in fact be encoded on a two-dimensional surface, much like the projection of a hologram. This concept challenges the very fabric of reality as we perceive it, hinting at a profound and hidden order underlying the cosmos. It suggests that the universe in all its complexity may operate according to deep informational rules, intertwining quantum mechanics with the architecture of space and time. As we delve deeper into these mysteries, the anthropic principle emerges as another lens through which to examine our universe's seemingly meticulous design. This principle confronts the striking observation that the fundamental constants and laws of physics appear to be exquisitely calibrated to support the emergence of life. From the precise strength of gravity to the delicate balance between electromagnetic and nuclear forces, the universe seems poised perfectly to allow stars, planets, and ultimately living organisms to form. Small deviations in any of these constants could render the cosmos sterile and lifeless. This realization fuels debate about whether our universe is uniquely suited for life or whether countless other universes exist, each with its own distinct physical rules, most incapable of supporting life. When considering the anthropic principle, one is compelled to confront staggering questions about purpose and existence. Some interpret the apparent fine-tuning of the cosmos as evidence of intentional design, a cosmic framework seemingly crafted to harbor life. Others propose a more detached perspective, suggesting that our presence in such a universe is a matter of observational selection. We could only ever observe a universe capable of sustaining us. This duality between perceived design and inevitable consequence drives a profound dialogue about the nature of cosmic purpose and the broader possibility of universes with radically different properties, potentially harboring life in forms we cannot yet imagine. Fine-tuning in physics further underscores this sense of wonder. Consider gravity. If it were marginally stronger, stars would burn out too quickly for life to develop. If slightly weaker, stars might never ignite. The strong nuclear force binding quarks into atoms must also fall within a narrow range to ensure stable matter. The fragile equilibrium of these constants has ignited a spectrum of interpretations. Some see in this balance the signature of an intentional cosmic design, perhaps even evidence of a creator. Others point to the multiverse, a staggering ensemble of universes, each with different laws, within which our life-permitting universe is a statistical inevitability. Skeptics caution that this fine-tuning may simply reflect observer selection bias. The universe seems precisely calibrated because we exist to notice it. Regardless, the discussion continues to stimulate both scientific inquiry and philosophical reflection on the purpose and nature of the cosmos. The anthropic principle manifests in several forms. The weak anthropic principle observes that our universe must possess conditions compatible with our existence, a statement grounded not in design but in observation. We are here to witness it. The strong anthropic principle goes further, suggesting that the universe's properties are such that life must inevitably arise at some point, hinting at a potential inherent purpose woven into the fabric of reality. The multiverse interpretation situates our universe among an unimaginable array of others, some hospitable, others barren, emphasizing probability rather than intent. The interplay between these ideas allows for a rich exploration of why our universe is precisely what it is, from the minuscule constants of nature to the vast structures of galaxies. When seen through the combined lens of multiverse theory and the anthropic principle, cosmic purpose takes on nuanced dimensions. Instead of implying a predetermined design, these perspectives suggest that the universe's apparent suitability for life may be a natural consequence of vast statistical possibilities across countless universes. What appears as intention could emerge from the probabilities inherent in the multiverse, where every conceivable combination of physical laws and constants can exist. This invites us to consider not just our own universe, but the innumerable potentialities that lie beyond, each offering different pathways for the emergence or absence of life. Fundamental constants form the cornerstone of this discussion. Immutable values, such as the speed of light, the gravitational constant, and the charge of the electron, dictate the operations of the cosmos with unerring precision. The fine-tuning argument emphasizes that even minute variations in these constants would render the universe unrecognizable. Weaker nuclear forces could prevent atoms from forming, stronger forces could preclude star formation, and slight shifts in gravity could lead to either cosmic collapse or runaway expansion. These exacting values inspire diverse interpretations: intelligent design, multiverse probability, or as yet undiscovered physical principles mandating these constants. Across physics, philosophy, and theology, these constants remain central to the inquiry into the cosmos's nature, fueling questions about the possible existence of other universes and the ultimate structure of reality. The concepts of observer selection bias and the anthropic principle intersect in subtle yet profound ways. Observer selection bias reminds us that our observations are inherently constrained by our own existence. We can only measure conditions in a universe where observers are possible. The anthropic principle formalizes this notion, noting that our very presence imposes constraints on the kinds of universes we can experience. Taken together, these ideas caution against overinterpreting the apparent rarity or precision of life-permitting conditions, framing the fine-tuning of the universe within a context of necessity and probability rather than pure accident. The concept of habitable zones, or Goldilocks zones, exemplifies these principles at a tangible scale. These regions around stars maintain the precise temperatures and conditions necessary for liquid water, a key ingredient for life as we know it. Earth's placement within the sun's habitable zone exemplifies this delicate balance, enabling a stable climate and the persistent presence of liquid water, essential factors for life's emergence and continuity. As astronomers discover more exoplanets within the habitable zones of other stars, the anthropic principle gains empirical grounding, illustrating how finely tuned environmental conditions underpin the potential for life throughout the cosmos. In tracing the interplay between quantum information, fine-tuning, the anthropic principle, multiverse theory, and habitable zones, one uncovers a tapestry of cosmic interconnections. These ideas challenge our assumptions about randomness, design, and inevitability, inviting a profound reconsideration of our place in the universe. From the infinitesimal precision of physical constants to the boundless possibilities of countless unseen universes, the cosmos emerges as a realm of staggering complexity, delicate balance, and profound mystery, where every discovery opens doors to questions far deeper than the answers themselves. Furthermore, the concept of habitable zones stretches far beyond the boundaries of individual star systems and unfolds on a grander galactic scale. Scientists call this the galactic habitable zone, a region within a galaxy where conditions may be favorable for the emergence of complex life. It is not only about a planet orbiting the right kind of star at the right distance. It is also about where that star itself is located within the vast architecture of the Milky Way. Too close to the crowded, radiation-filled galactic center, and conditions are hostile, too far toward the galactic edges, and heavy elements needed for rocky planets and biological chemistry are scarce. This broader view ties directly into the anthropic principle, the idea that our very existence as observers may be linked not just to our solar neighborhood, but to our specific placement within the galaxy itself. The rare Earth hypothesis and the idea of cosmic fine-tuning are often interwoven in this discussion. The rare Earth hypothesis proposes that the unique blend of conditions that gave rise to complex life on our planet may be staggeringly uncommon across the universe. This possibility finds resonance in cosmic fine-tuning, the observation that the fundamental constants of nature appear to be adjusted with extraordinary precision to allow for life. The strength of gravity, the mass of fundamental particles, the balance of forces that govern atoms and stars, the speed at which the universe expands. All of these values exist within a narrow band that permits galaxies, stars, planets, and eventually life itself. If gravity were just a little weaker, galaxies might never have formed. If it were stronger, stars might collapse too quickly for life to evolve. A slightly altered rate of cosmic expansion could have rendered the universe sterile or prevented it from existing in any recognizable form. On Earth, the picture grows even more intricate. Our planet orbits within the sun's habitable zone, but that alone does not explain our flourishing biosphere. Earth has a large moon, stabilizing its axial tilt and moderating climatic extremes. It has a magnetic field, born of its molten iron core, shielding the surface from deadly solar and cosmic radiation. Its atmosphere has just the right mixture of gases to regulate temperature and allow organisms to breathe, while also filtering harmful radiation. Plate tectonics recycle carbon and foster long-term climate stability. Oceans cover much of the surface, providing an environment where life could begin and diversify. Taken together, this extraordinary balance may represent an exceedingly rare cosmic lottery win. These ideas invite reflection on whether Earth is truly unique or simply one rare case among countless possibilities. They remind us of how improbable our existence might be and how finely balanced the conditions for life appear to be in the vast immensity of the cosmos. Even if we are not alone, these concepts underscore the fragile and extraordinary set of circumstances that sustain us. One of the most pressing puzzles in this conversation is the cosmological constant problem. Quantum field theory predicts that empty space is not truly empty. Instead, it seethes with virtual particles that appear and vanish in a ceaseless froth of energy. If this vacuum energy were added up according to theory, the result would be so immense that the universe should have expanded catastrophically fast, tearing itself apart long before galaxies or stars could form. Yet, astronomical observations reveal something profoundly different. The actual expansion of the universe is much gentler, with a vacuum energy density vastly smaller than theoretical predictions. The mismatch between theory and observation is staggering, greater than 100 orders of magnitude. This discrepancy has become one of the central mysteries of physics, highlighting the need for an unknown mechanism that reduces the energy to just the right value for a stable, life-permitting cosmos. To many, this seems like one of the clearest signs of fine-tuning in the universe. Here, the anthropic principle enters once again. It suggests that the universe must, by definition, allow for the existence of beings capable of asking these questions. When applied to the search for extraterrestrial life, it shapes both our methods and our expectations. Because we evolved on Earth, we instinctively search for worlds resembling our own. Planets with liquid water, atmospheres rich in oxygen and carbon dioxide, moderate climates where chemistry can flourish. Yet the anthropic principle also challenges us to look beyond these biases. Life may not always resemble the patterns we know. The methane lakes of Titan, the subsurface oceans hidden beneath the icy crusts of Europa and Enceladus, or even environments we can scarcely imagine may harbor alien biochemistries. This principle also influences our thinking about how common or rare life might be. If intelligent life is exceedingly rare, then humanity may represent one of the first sparks of awareness in the cosmos. That could explain why we have not yet detected signals from others. On the other hand, if life is abundant, then the silence of the skies raises troubling questions. Perhaps civilizations tend to destroy themselves before spreading across the stars. Perhaps the hurdles to long-term survival are far higher than we hope. The tension between these possibilities frames what is often called the Fermi paradox. If life is common, why do we not see it? Beyond these debates lies an even deeper speculation, the idea that the universe itself may not be singular. Theories of cosmic cycles propose that creation and destruction may be woven into the fabric of existence. In some models, universes are born in a blaze of expansion, grow over immense timescales, and eventually collapse, only to give rise to new universes in an endless sequence of rebirth. Over billions of years, this cosmic recycling increases the richness of galactic environments, enabling the rise of new structures, worlds, and potentially even life itself. The life of a star, though brief compared to cosmic time, is part of a perpetual system of renewal. The universe remains dynamic, never stagnant, continually rearranging its own building blocks to create conditions for new phenomena to emerge. Galaxies, too, follow their own cycles. Born from vast reservoirs of gas and dust, they evolve over billions of years, hosting generations of stars that live and die within them. Their growth is shaped not only by internal processes, but also by collisions and mergers. Smaller galaxies combine into larger ones. Giant galaxies absorb their neighbors. These colossal encounters spark bursts of star formation, accelerating the cosmic cycle of creation and destruction. In time, many galaxies transform into massive ellipticals, exhausted of gas, their star-making days largely behind them. Beyond individual galaxies lies an even larger stage. Galaxies cluster together into filaments and nodes, forming a cosmic web that stretches across the observable universe. Vast voids open between these structures, while gravity draws matter along the filaments into denser regions. This architecture evolves on incomprehensible scales of time, reminding us that cycles occur not only in stars and galaxies, but also in the very structure of the universe itself. Studying galactic evolution allows us to trace how matter and energy flow, connect, and reshape reality on every level, from the smallest clouds of gas to the largest clusters of galaxies. Within this grand theater, black holes play a paradoxical role. They are both destroyers and creators, consumers and recyclers. A black hole swallows matter and even light, trapping anything that strays too close. Yet the process is not only destructive. Matter falling into a black hole often forms a blazing accretion disk, heating to extraordinary temperatures and releasing radiation powerful enough to influence star formation and galactic dynamics far beyond its immediate surroundings. Some black holes unleash jets that stretch across intergalactic space, carrying matter and energy outward to seed and stir distant regions. Supermassive black holes at the centers of galaxies are especially significant. They regulate the growth of their host galaxies, maintaining a delicate balance between expansion and stability. They are not simply silent voids, but active participants in cosmic evolution, engines of transformation that redistribute matter and energy on scales almost too vast to grasp. In theoretical models, black holes may even connect distant regions of space-time through exotic structures, such as wormholes, hinting at possibilities beyond our current understanding. All of these cycles, stars, galaxies, black holes, point toward a universe in constant motion, always creating, dissolving, and recreating. The concept of a cyclic universe magnifies this vision. Instead of a single creation event or a definitive end, the universe may expand and contract endlessly, rebirthing itself again and again across timescales that stretch trillions of years. Our present universe, under this view, is only one chapter in an infinite series. What is the purpose of such an arrangement? Perhaps it is not about a destination, but about persistence, not about a singular goal, but about the eternal act of becoming. Each cycle reshuffles the deck, allowing new structures, new possibilities, and perhaps new forms of life and consciousness to emerge. Some theories even suggest that each universe may inherit subtle imprints from the one before it, carrying forward traces of information or complexity. If so, then the cosmos itself might be learning, evolving, and growing across cycles, building towards something greater in ways we cannot yet fathom. In that sense, the purpose of the universe might not lie in a final answer, but in the unending cycle of renewal. Creation, transformation, dissolution, and rebirth, again and again, an eternal rhythm that ensures existence never ceases, only changes form. However, it is important to note that the cyclic universe model remains a theoretical construct. an idea not yet supported by direct evidence, but compelling enough to inspire some of the most ambitious questions ever asked about existence itself. The suggestion that the universe might not be a one-time event, but part of an eternal rhythm of death and rebirth carries with it both scientific intrigue and philosophical weight. Yet, our understanding is still limited. The ultimate fate of the cosmos, whether it expands forever, collapses back into itself, or oscillates in a never-ending series of cycles, remains unresolved. The pursuit of this answer fuels some of the most exciting research in both cosmology and theoretical physics, where equations and observations are continuously tested against the vast silence of space. Matter and antimatter interactions hold a central place in this mystery. In the earliest instance after the Big Bang, the universe existed as a seething ocean of unimaginable heat and density, a primeval fire where particles and antiparticles were born in pairs, only to annihilate one another in flashes of pure energy. This was no simple process of destruction, but a cosmic equilibrium, a balance that governed whether anything permanent could survive. Out of this dynamic struggle, a minute imbalance tipped the scales. For every billion antimatter particles, there existed 1,000,000,001 matter particles. That tiny excess determined everything. As matter and antimatter collided and vanished in bursts of radiation, that sliver of surviving matter endured. From it would arise stars, galaxies, planets, and eventually life itself. This imbalance is known as baryogenesis, and it remains one of the deepest mysteries in physics. Why matter prevailed when it should have been extinguished alongside antimatter is still unanswered. Scientists probe this enigma, building particle accelerators, studying high-energy collisions, and searching for asymmetries in nature that might explain why existence itself was favored over nothingness. The echoes of those annihilations still shine in the cosmic microwave background, a faint afterglow that whispers the story of creation to any who can listen. Theories of cosmic rebirth take these questions and cast them onto a canvas of staggering scale. Eternal inflation suggests that our universe is but one bubble among an infinite sea, each bubble forming in an ever-expanding fabric that knows no bounds. In this vision, universes continuously bloom like foam on a cosmic ocean, each isolated, each distinct, each perhaps governed by its own physical laws. Some may flicker out quickly, lifeless and inert. Others may endure, giving rise to stars, chemistry, and consciousness. This idea challenges the notion of a single universe with a defined beginning and end. It proposes instead a multiverse, where universes are tested like experiments in a boundless laboratory of existence. Philosophers and scientists alike speculate whether such an endless unfolding serves a purpose, maximizing diversity, ensuring the emergence of life, or simply existing without reason. Yet to assign purpose is to step outside science into philosophy. What can be said is that eternal inflation redefines our place in the cosmos, shifting the question from why our universe exists to why this universe, among countless others, holds the conditions we know. Amid these grand theories, the violent lives of stars remind us of creation's immediacy. Supernovae, the explosive deaths of massive stars or unstable white dwarfs, unleash energy and forge elements that the universe could not produce otherwise. In their fiery deaths, gold, silver, uranium, and countless other heavy elements are born. These stellar corpses scatter their creations across interstellar space, seeding the material from which new stars and planets will form. Without these explosions, the cosmos would be a barren place of hydrogen and helium, incapable of sustaining the chemistry of life. The shock waves of supernovae ripple through gas clouds, igniting the birth of new stars, weaving cycles of destruction and renewal into the very fabric of galaxies. Each explosion, though cataclysmic, is also a moment of profound creation. The atoms in our bodies were once forged in these ancient furnaces, linking us forever to the stars that perished long before Earth was born. Cosmic inflation ties these cycles together, offering a bridge between the universe's explosive beginning and the possibility of endless creation. In the briefest sliver of time after the Big Bang, space itself expanded faster than light, stretching quantum fluctuations into the seeds of galaxies. Some cosmologists argue that inflation is not a singular event, but a repeating process, spawning new universes wherever pockets of inflationary expansion ignite. In this framework, the multiverse is not static but dynamic, a branching tree where each offshoot becomes a universe of its own. Each universe could expand, evolve, and in turn give birth to others, perpetuating an eternal cascade of creation. Though untestable with our current tools, this idea reshapes the question of beginnings. The cosmos may never have had a single origin at all, but instead may exist as a ceaseless flowering of universes, each carrying its own destiny. The dance of galaxies provides yet another testament to cosmic cycles. When galaxies collide, their shapes distort, their stars are cast adrift, and titanic waves of gas collapse into brilliant bursts of new star formation. Though destructive in appearance, these collisions are essential to galactic evolution. They weave together histories of countless stars, merging dust, gas, and energy into new forms. Our own Milky Way is not exempt from this process. In billions of years, it will merge with the Andromeda Galaxy, forming a new, larger galactic system bathed in fresh stellar light. Observing these events across the cosmos reveals not chaos, but rhythm. Death gives way to birth, destruction to creation, and endings to new beginnings. In this way, whether in the annihilation of particles, the explosions of stars, the merging of galaxies, or the inflation of entire universes, the cosmos reveals itself as a vast interplay of cycles. Each scale tells the same story. Destruction is not final, but transformative, an act of renewal written into the very structure of reality. Moreover, galaxy mergers demonstrate not only the interconnectedness of cosmic structures, but also the ceaseless vitality of the universe itself. The gravitational choreography of these colossal encounters shows how galaxies, some containing hundreds of billions of stars, collide, merge, and transform. In this slow yet relentless process, the very fabric of the cosmos is reshaped, weaving together a vast network of matter that stretches across billions of light years. Every merger tells a story of destruction and creation, of ancient stars being torn apart, while new generations of stars are born from recycled gas and dust. These cataclysmic encounters highlight a universe that refuses stasis, instead existing in perpetual renewal. The cycle is unmistakable. From the moment ancient stars lived and died, they scattered heavy elements into space. When galaxies merge, these elements are swept up, compressed, and forged into new stellar systems, continuing the chain of stellar birth and death. Out of this cosmic recycling emerged everything we know, including the raw ingredients that eventually led to our own existence on Earth. While questions about purpose remain firmly in the realm of philosophy, what is evident is that galaxy mergers reveal a universe committed to reinvention, where the end of one structure is the beginning of another. Dark matter is central to this story. Though invisible, intangible, and immune to interaction with light, it exerts a gravitational grip that holds the universe together. It is the unseen scaffold on which galaxies are built, the hidden framework that supports the cosmic web. Scientists cannot see it directly, but its influence is undeniable. The way galaxies rotate, the binding of galaxy clusters, and the large-scale distribution of matter all point to the presence of something powerful and unseen. Dark matter is the silent architect, guiding ordinary matter into vast filaments and nodes that span the universe, organizing the raw chaos of creation into coherent structure. Since the earliest moments after the Big Bang, dark matter played a critical role. It provided the seeds that allowed matter to clump and collapse into the first stars and galaxies. Without it, the cosmos might have been a far emptier place, a nearly uniform expanse without the grand structures we see today. The very existence of galaxies, galaxy clusters, and ultimately habitable worlds is tied to the presence of this mysterious substance. Its role sparks profound questions. It may lack purpose in a theological sense, yet its ubiquity suggests it is indispensable to the cosmic story. Studying dark matter continues to push the boundaries of human understanding, forcing us to confront how little we truly know about the foundation of our universe. Dark energy adds yet another layer of mystery. Unlike gravity, which pulls, dark energy pushes, stretching the fabric of space itself. It is everywhere, permeating the cosmos, and it drives galaxies apart at an ever-increasing rate. Discovered in the late 1990s through the study of distant supernova, dark energy overturned the long-held belief that cosmic expansion would slow under gravity's influence. Instead, the universe is accelerating outward. This revelation reshaped cosmology, suggesting that the ultimate fate of the universe may not be collapse, but dispersal. The implications are staggering. If dark energy continues to dominate, the cosmos may face the Big Freeze, a future in which galaxies drift so far apart they can no longer see one another. Stars will burn out, leaving behind cold remnants scattered across an ever-expanding void. Over unimaginable timescales, the universe would become silent and empty, a place where matter and energy no longer interact in meaningful ways. Yet, despite its profound impact, the nature of dark energy remains elusive. Scientists strive to uncover its properties, knowing that doing so could revolutionize our understanding of space, time, and the destiny of everything that exists. Together, dark matter and dark energy shape the grand architecture of the cosmos. Dark matter provides the skeleton, anchoring galaxies and weaving the cosmic web, while dark energy drives the expansion, pulling everything apart on the largest scales. Their interplay forms the backdrop against which all cosmic history unfolds. Though invisible, these forces dominate the universe, accounting for the vast majority of its contents, leaving ordinary matter, the stars, planets, and people we can see, as only a small fraction of reality. The cosmic web itself reveals the grandeur of this architecture. Spanning billions of light years, it forms a vast network of filaments and voids, with galaxies strung along like beads on threads of dark matter. At the intersections of filaments lie colossal galaxy clusters, gravitational giants that mark the densest nodes of this web. Observations and computer simulations show that dark matter forms the backbone of this structure, guiding visible matter into place and shaping the universe into a tapestry of rivers, intersections, and vast empty expanses. By studying the cosmic web, scientists not only learn about dark matter, but also test theories of gravity and probe the mysterious nature of dark energy. Dark flow adds yet another enigmatic chapter. It suggests that galaxy clusters across immense regions of space may be moving in a common direction, as though drawn by some unseen gravitational source beyond the observable universe. This idea arose from subtle patterns in the cosmic microwave background, the faint afterglow of the Big Bang. If confirmed, dark flow would imply that structures larger than our cosmic horizon exist, exerting influence across distances we cannot yet observe. Such a phenomenon challenges the principle that the universe is uniform and isotropic on the largest scales, principles that underlie modern cosmological models. If dark flow is real, then the universe is far more interconnected and complex than previously imagined. It would mean that even beyond what we can see, the cosmos continues to influence itself in ways we are only beginning to glimpse. In the end, galaxy mergers, dark matter, dark energy, the cosmic web, and dark flow all converge into a single narrative. The universe is alive with motion, complexity, and mystery. It is not static, but dynamic, a place where hidden forces sculpt visible wonders, and where each discovery only deepens the sense that we are part of something far greater than we can yet comprehend. However, the existence of dark flow remains debated in the scientific community, a cosmic enigma that divides researchers between skepticism and cautious acceptance. Some studies have failed to detect its trace, suggesting it may be nothing more than an observational illusion, while others continue to uncover tantalizing signals that hint at vast, unseen currents tugging entire clusters of galaxies across the universe. As technology evolves and telescopes grow sharper, humanity pushes closer to clarity, hoping to determine whether dark flow is a profound truth written into the fabric of space-time or a fleeting error in our cosmic measurements. Dark matter, equally invisible and mysterious, plays an undeniably crucial role in shaping the very framework of the universe. Though it neither shines nor reflects, it exerts a gravitational pull that binds galaxies together and molds the skeleton of cosmic structure. Without this hidden mass, galaxies might never have formed in the stable, graceful spirals we see today. Their stars could have drifted apart, leaving a chaotic, inhospitable void. Instead, dark matter halos cradle galaxies in protective cocoons, preserving their structure, governing their rotation, and ensuring their long-term stability. Within these galaxies, stars are given the time they need to ignite, planets to coalesce, and conditions to develop that may ultimately allow life to emerge. In this way, the unseen becomes essential, a silent architect of worlds that might harbor consciousness. The reach of dark matter is not limited to isolated galaxies. On the grandest scales, its gravity weaves a colossal cosmic web, stretching filaments of matter across the universe and carving out immense voids where few galaxies exist. This vast structure determines where stars and planets can form, creating patterns that indirectly dictate the locations where habitable environments might appear. Although dark matter does not interact with atoms, molecules, or the elements of life directly, its influence orchestrates the conditions necessary for life to arise. Its invisible hand has sculpted the stage upon which the drama of existence unfolds, guiding galaxies into clusters, clusters into superclusters, aid and building the environments where worlds like our own can take shape. Yet, even as dark matter secures the foundations of cosmic order, another force works to unravel it. Dark energy, discovered in the late 1990s, revealed a startling truth. The universe is not only expanding, but doing so at an ever-increasing rate. The discovery shocked astronomers, overturning the long-held belief that gravity alone governed the universe's ultimate fate. Instead, this mysterious force accelerates the separation of galaxies, stretching the cosmos wider and colder with each passing eon. The trajectory seems clear. The universe races toward a future of thin emptiness, where stars fade, galaxies drift into isolation, and the cosmic night deepens into silence. This vision of a heat death, where maximum entropy reigns and complexity dissolves into uniformity, raises unsettling questions about purpose. Science can measure, calculate, and predict, but it cannot answer why. The balance of dark energy and gravity has allowed galaxies, stars, and life itself to form, yet the same force may drive all things toward eternal darkness. Some ask whether intelligence is a fleeting accident in cosmic history, a brief flicker of awareness soon extinguished. Others wonder if life, consciousness, and purpose might be woven into the very fabric of the universe, waiting to emerge again and again, wherever conditions allow. Such questions transcend equations, blurring the line between science and philosophy. Amid these mysteries, gravitational lensing offers a window into the invisible. When colossal objects like galaxy clusters bend the light of more distant galaxies, they create distorted arcs and duplicated images. These distortions reveal the hidden mass that light cannot touch, providing some of the strongest evidence for dark matter. Astronomers studying these patterns find gravitational effects far stronger than what visible matter alone could explain, confirming the presence of vast quantities of unseen material shaping the universe. By mapping these distortions across the sky, scientists can trace the dark matter filaments that form the cosmic web itself, a vast scaffolding that holds the galaxies in place. Gravitational lensing is more than a method of observation. It is a test of reality. Competing theories of modified gravity attempt to explain cosmic behavior without invoking dark matter, but the lensing effects provide a decisive challenge. By comparing predictions with what is seen in the distorted light of distant galaxies, astronomers evaluate these alternatives, refining our understanding of the universe's most fundamental forces. Each lensed arc of light becomes a clue, each warped galaxy a piece of evidence in the search for truth. Dark energy, meanwhile, stands as the greatest uncertainty in the universe's long-term fate. If it remains constant, the cosmos will expand endlessly, galaxies receding until their light can no longer reach one another. Stars will exhaust their fuel, planets will grow cold, and the universe will drift into an eternal big freeze. If dark energy strengthens, it could lead to an even more dramatic conclusion: the Big Rip. In this scenario, galaxies are torn apart, then stars, then planets, and finally even the atoms themselves, as space stretches faster than anything can resist. In these possibilities lies the ultimate paradox of existence. The same forces that created galaxies, stars, and the chance for life may also ensure their destruction. The universe writes and erases its own story, leaving us to wonder whether meaning exists within the cycles of creation and dissolution. From the hidden presence of dark matter to the relentless push of dark energy, the cosmos reveals itself as both cradle and executioner, a stage set for life, but destined for silence. And in that silence, humanity searches for understanding, tracing light across the void, chasing patterns in the dark, and confronting the mysteries that define both the universe and ourselves. However, If dark energy weakens or alters its behavior, entirely new destinies for the cosmos emerge from the shadows of possibility. A diminishing dark energy could set the stage for a catastrophic Big Crunch, a future where gravity triumphs over expansion, pulling galaxies, stars, and all of space itself inward until everything collapses in a fiery end. In another scenario, the universe may not simply die, but instead breathe in cycles, expanding outward only to contract again, reborn in an endless rhythm of destruction and creation, a cosmic heartbeat echoing across eternity. The mysterious force of dark energy not only dictates the ultimate fate of the universe, but also governs the very architecture of cosmic structures. Its repulsion counters gravity's embrace, restraining the growth of massive galaxy clusters and sculpting the sprawling web of matter that spans the heavens. It is here, in this silent conflict between expansion and attraction, that the grand design of the cosmos is drawn. Dark matter halos stand at the center of this story. Though invisible, they are immense guardians surrounding galaxies and clusters, their unseen mass bending the paths of stars and shaping the dance of cosmic matter. These halos are scaffolds of gravity, the unseen skeletons on which galaxies take form. Gas, dust, and stars gather within their depths, binding together to create the brilliant spirals and vast ellipticals that light up the night. The relationship between dark matter halos and galaxies is one of interdependence, a silent symbiosis. Galaxies grow within the confines of their halos, nurtured and constrained by their invisible cages. In turn, the halos evolve by merging with one another and by drawing in matter from the intergalactic sea. This process gives rise to the intricate cosmic web, where great halos host massive galaxies, while smaller halos cradle dwarf galaxies or remain unseen in eternal darkness. The presence of these halos shapes not only where galaxies exist, but also how they live, influencing gas flows and the birth or suppression of stars. Through this interplay, dark matter halos become indispensable storytellers in the saga of cosmic structure. They are the framework that allows galaxies, stars, and planets to emerge, setting the stage for complexity, for chemistry, for biology, and for thought itself. Without them, the universe would be a barren expanse, devoid of the intricate variety we now observe. In their silent gravitational grip, they hold the key to understanding how order arises from chaos, and how the cosmos evolved into its present grandeur. Yet as vast as dark matter is, it is quantum mechanics that draws us down into the smallest realms, revealing a reality stranger than myth. Here, certainty dissolves and the laws of probability reign. At the quantum scale, particles can exist in many states at once, a shimmering blur of possibilities collapsing into a single reality only when observed. This phenomenon, superposition, tells us that reality is not fixed but contingent, shaped by the act of measurement itself. The implications stretch far beyond atoms and electrons. Some scientists suggest that the universe itself may operate on quantum principles, with multiple futures hovering in potential until they resolve into a single outcome. Such speculation opens profound questions about consciousness, about free will, and about whether our choices are threads in a tapestry already woven or still being created. Even more astonishing is quantum entanglement, where particles remain connected across vast distances, instantaneously mirroring one another regardless of separation. This challenges our deepest understanding of space and time, hinting that division itself may be an illusion, and that the cosmos is bound together in ways we cannot yet grasp. In this vision, the universe is less a collection of isolated objects and more a network of interwoven relationships, suggesting that interconnectedness may be a fundamental truth of existence. Entanglement does not merely exist in the abstract. It underpins the bonds of atoms, the formation of molecules, and the chemistry that builds stars and life. On the cosmic scale, it may hold clues to the mysteries of black holes. Some theories propose that entanglement is the key to the black hole information paradox, preserving knowledge once thought lost beyond the event horizon. Others go further, speculating that entanglement itself may weave the very fabric of space-time, giving rise to the dimensions in which we live. Equally mind-bending is the many worlds interpretation of quantum mechanics, which suggests that every possible outcome of every quantum event unfolds in its own separate universe. In this view, our universe is only one of countless parallel realities branching infinitely with every interaction. Here the idea of purpose grows slippery. If all outcomes occur, is there still meaning in any single one? Some argue yes, that the infinite expansion of possibility fulfills a higher goal of manifesting all realities. Others counter that such endless variation robs meaning from any particular universe, leaving purpose and illusion stretched too thin to hold. Another quantum phenomenon, tunneling, lies at the heart of both cosmic beginnings and stellar lives. Tunneling allows particles to slip through barriers deemed impenetrable by classical physics. In the earliest fraction of a second after the Big Bang, a tunneling event may have triggered cosmic inflation, unleashing a storm of expansion that shaped everything to come. Today, tunneling fuels the nuclear fusion in stars, allowing protons to overcome their mutual repulsion and ignite the furnaces that shine across the galaxies. Without tunneling, stars would not burn, heavier elements would never form, and life would not exist. Tunneling also gives rise to Hawking radiation, enabling particles to escape black holes, causing them to evaporate over unimaginable timescales. In this way, tunneling connects the smallest quantum rules with the largest gravitational giants, hinting at a bridge between two realms of physics that remain stubbornly divided. Finally, there is the uncertainty principle, the haunting truth discovered by Werner Heisenberg. It declares that certain properties of particles, such as position and momentum, cannot be known with perfect accuracy at the same time. The more clearly we see one, the more the other fades into obscurity. This is not a failure of instruments, but a fundamental feature of reality. On the scale of the universe, it means that uncertainty is woven into the fabric of existence, that the cosmos resists prediction, and that destiny itself may be unknowable. This unpredictability challenges the notion of a predetermined cosmic purpose. If the universe itself trembles with uncertainty, then perhaps its meaning is not a single path etched into stone, but an unfolding story, one where chance, probability, and possibility all have their place. And in this vast interplay between dark energy and dark matter, between entanglement and uncertainty, between expansion and collapse, the universe continues its enigmatic performance, inviting us to wonder not only about its fate, but about our own place within its ever-changing design. Furthermore, the uncertainty principle suggests that the simple act of observing an experiment can alter its outcome, reshaping not only our data, but our very conception of existence. This subtle yet profound truth forces us to confront unsettling questions about our role in the cosmos. Are we passive witnesses, or does our awareness weave itself into the fabric of reality, rewriting the story of the universe each time we look more closely? The principle itself undermines the notion of an immutable, objective reality and hints that the quest for cosmic meaning may be inseparable from our presence within it. Knowledge, once thought of as a clear path toward ultimate truth, becomes instead a shifting horizon. We reach for it, we study, we probe deeper, and yet the principle reminds us that certain elements of existence may forever evade us. Mystery is not just a temporary obstacle, it is a permanent feature of reality. Yet, this uncertainty does not extinguish the possibility of cosmic purpose. It suggests instead that purpose, if it exists, may reveal itself not as a fixed answer, but as an evolving understanding, a purpose that changes alongside our growth and discoveries. Beyond this philosophical edge, quantum coherence emerges as a startling bridge between the subatomic and the biological. Traditionally confined to the dance of electrons and photons, coherence has revealed itself in the living world in ways that astonish scientists. Processes like photosynthesis are no longer viewed as purely mechanical transfers of energy, but as performances choreographed at the quantum level. In plants, light harvesting complexes appear to channel photons through pathways of coherence, guiding energy to reaction centers with precision and efficiency far beyond what classical physics would predict. This quantum orchestration allows organisms to draw upon sunlight with breathtaking effectiveness, a survival advantage written into the very mathematics of their existence. In the migration of birds, researchers suspect that avian navigation taps into quantum entanglement, letting creatures read the Earth's magnetic fields with uncanny accuracy. Such findings blur the once firm boundaries between the living and the quantum, suggesting that biology itself may be infused with principles that echo the foundational structures of the universe. These revelations stir grander questions. If coherence can shape life, might it also be integral to life's emergence? Could quantum processes be the hidden thread that allowed matter to cross the threshold into biology, transforming chaos into order and order into consciousness? Some scientists dare to propose that life is not an accident scattered in the void, but a participant in a larger unfolding, a cosmic push toward greater complexity and deeper networks of information. If this is true, life is not merely surviving within the universe, but contributing to its evolution, playing an active role in the grand architecture of reality. Quantum field theory then enters this narrative as a monumental achievement of human thought, giving us the tools to see particles not as isolated beads, but as excitations in invisible fields that saturate space. Matter becomes a ripple, a vibration, a fleeting surge in an endless continuum. Through this lens, phenomena like particle creation and annihilation are no longer esoteric curiosities. They are expected consequences of fields in motion. This framework lies at the heart of the standard model of particle physics, an edifice that describes with extraordinary accuracy the interactions among the known forces of nature, leaving gravity alone as the great outsider. The early universe, with its unimaginable heat and density, becomes a stage where these interactions shaped everything we see today, from the clusters of galaxies to the carbon in our bones. Even the vacuum, long mistaken for emptiness, is revealed as a cauldron of restless activity. Virtual particles flicker in and out of being, ephemeral yet essential. They are messengers of forces, guardians of structure, and perhaps the very architects of cosmic fate. In the first fractions of a second after the birth of the universe, these particles may have driven inflation, an exponential expansion that stretched the fabric of space-time itself. Their fleeting presences seeded the primordial irregularities that gravity later sculpted into galaxies, stars, and planets. Without them, the night sky might be dark and barren. These ghostly entities also haunt the edges of black holes. Stephen Hawking proposed that when pairs of virtual particles arise near the event horizon, one can be swallowed while its partner escapes, robbing the black hole of mass. Over immense timescales, this process, Hawking radiation, implies that even the mightiest gravitational prisons are not eternal. They, too, dissolve into the quantum haze. The implications are staggering. The death of black holes, the reshaping of cosmic energy, the eventual whisper of information back into the void. Layered beneath all this is the concept of quantum foam, the restless underpinning of space-time itself. At scales smaller than atoms, smaller even than quarks, space-time loses its smoothness and becomes a seething broth. It bubbles, froths, writhes in constant transformation. Instead of a continuous stage upon which events unfold, space-time itself is reduced to a granular storm where measurement breaks down, where certainty evaporates, and where the boundaries of knowledge are crushed beneath quantum turbulence. This foam could be the deep reservoir from which everything springs, the raw texture of being. It may connect directly to dark energy, fueling the universe's accelerating expansion, or even offer the first hints toward quantum gravity, the long-sought theory that will unite the physics of the vast with the physics of the minuscule. In confronting these mysteries, our perspective widens. We are not separate from these forces, nor immune to their implications. We live inside the interplay of coherence and uncertainty, particles and fields, foam and expansion. Each breath we take is entangled with photons born in the hearts of stars, each thought powered by processes that echo the quantum symphony discovered in leaves and in birds. The pursuit of understanding carries us deeper, but each layer peels back to reveal yet more strangeness. Reality resists finality. The fabric of the universe remains restless, evolving, and forever beyond complete capture by our finite minds. And yet it is within this very incompleteness, this balance of wonder and limitation, that our search for purpose persists, weaving us into the ever-expanding story of the cosmos. However, in the most extreme realms of existence, such as the earliest instance after the birth of the universe or deep within the event horizons of black holes, the two great frameworks of modern physics collide. Quantum mechanics, which governs the behavior of the smallest particles, and general relativity, which explains the vast geometry of space and time, both exert their influence with equal force. Yet, when they meet, they do not align. The quest for a theory of quantum gravity seeks to reconcile this clash, promising to illuminate the hidden mechanics of the cosmos under the most unforgiving conditions. Such a theory could provide us with a lens into the nature of reality itself, peeling back the veil on mysteries that have lingered since humanity first looked upward and wondered. One of the most tantalizing possibilities lies in addressing the riddle of the universe's birth. Could quantum gravity describe a cosmos before the Big Bang, before time itself began its march? Might it explain what lies beyond the singularity, that seemingly impossible point of infinite density where known physics collapses into silence? If so, we would be forced to rethink the very nature of beginnings, the essence of space, time, and causality. What today appears as an unapproachable wall in our knowledge may instead reveal itself to be a doorway into a deeper truth about existence. The implications stretch further. Quantum gravity may carry within it the key to puzzles that haunt cosmology. The elusive essence of dark matter, invisible yet binding galaxies together, and the enigmatic force of dark energy, pushing the universe apart at an accelerating pace. By uniting the subatomic with the cosmic, such a framework could reveal a hidden order, connecting the behavior of particles with the architecture of the largest structures in the universe. This union might offer not only elegance but also completeness, a way of describing the totality of reality in a single language. Yet even with such a theory, questions remain about where the universe is heading. The expansion we observe today, driven ever faster by dark energy, leads us to consider different destinies. Each possibility is both scientific and philosophical, raising profound questions about meaning, permanence, and the very purpose of existence itself. The scenarios stretch across a spectrum of outcomes, from infinite coldness to violent collapse, from cyclical rebirth to ultimate disintegration. One haunting vision is the Big Freeze. In this picture, expansion never ceases. Galaxies drift apart until they vanish beyond one another's horizons. Stars exhaust their fuel one by one until the night sky grows black. Matter decays and even protons eventually disintegrate. What remains is a cosmos of unimaginable emptiness, a thin soup of particles and radiation spread so evenly that no further change can occur. The universe, in this fate, has no dramatic finale, only silence, a march toward maximum entropy. Yet this scenario, stark as it may be, offers a strange kind of beauty. It emphasizes the rarity and preciousness of the present, a fleeting age in which galaxies shine, life arises, and consciousness reflects upon its place in the whole. The Big Freeze reminds us that our moment, though brief, is extraordinary. Another possibility is the Big Crunch. Here, gravity eventually overcomes the outward rush of expansion. The universe, once vast and cold, halts, then contracts. Galaxies race back toward each other, stars collide, temperatures rise. At last, all matter and energy collapse into a singularity, a searing point of density and heat. Some imagine this as an end. Others see it as a beginning, a cyclical universe in which every death births a new creation, a cosmic heartbeat without end. Such cycles echo patterns already familiar: the seasons of Earth, the life and death of stars, the endless renewal of nature. If reality is cyclical, then perhaps there is a deeper rhythm to existence, one that transcends the boundaries of human comprehension. Heat death, a concept grounded in thermodynamics, presents another chilling scenario. Entropy, the measure of disorder, always rises in a closed system, and the universe itself is the ultimate closed system. Over immense timescales, black holes evaporate through Hawking radiation, stars fade into darkness, and every difference in temperature is erased. In this vision, no work can be done, no change can occur, no life can endure. It is a cosmos without events, timeless in its stillness. Yet even here, thinkers speculate. Might new universes bud from the ashes? Could advanced civilizations harness dark energy to resist the inevitable? Though the idea is sobering, it forces us to confront the fragility of everything we know and to see existence as both fleeting and precious. The most dramatic scenario is the Big Rip. If dark energy continues to accelerate unchecked, its power might not stop at tearing galaxies apart. It could unravel stars, planets, molecules, even atoms. The fabric of space-time itself would be rent, and the universe would dissolve into an empty void. Such an ending is terrifying in its finality, yet it also compels reflection. If all structures are impermanent, what then is meaning? Perhaps meaning lies not in permanence, but in experience, in the fleeting moments of order that emerge from the chaos. All of these possibilities, the freeze, the crunch, the heat death, the rip, reveal more than cosmic mechanics. They are mirrors reflecting humanity's deepest questions. Is there purpose in the universe? Or is purpose something we create, small sparks of meaning in an indifferent expanse? The ultimate fate of the cosmos remains uncertain, but the very act of contemplating it binds us to the grand story of existence. Whether the universe ends in silence, fire, renewal, or dissolution, we are participants in its unfolding, witnesses to a mystery as vast as time itself. However, the Big Rip scenario also invites us into a narrative of staggering depth, one that underscores the ceaseless dynamism of the cosmos. It reminds us that the universe is not a still canvas, but a living process, unfolding in rhythms and scales that defy ordinary perception. Every galaxy, every star, every planet, even the atoms that make up the human body, are temporary participants in this vast choreography of expansion and change. To consider such an ultimate unraveling is to recognize the fragile brilliance of the present, to marvel at the fact that structured order exists at all in a reality where impermanence seems written into the very laws of nature. The thought that one day every star, every molecule, every link in the chain of existence could be torn apart lends a heightened preciousness to the now, elevating the value of the fleeting forms we see around us. This sense of impermanence is mirrored in another profound possibility, the idea of vacuum decay. Rooted in the framework of quantum field theory, it paints a vision of the universe that is not necessarily secure in its current form. According to this concept, what we perceive as stable reality may in fact rest in a precarious balance, a false vacuum state. Within the layered structure of quantum fields, lower energy states might exist that are more stable than the one in which our universe currently resides. Should even a minuscule region of space slip into this deeper state, it could trigger a chain reaction of astonishing consequence. A bubble of true vacuum could form and expand at nearly the speed of light, rewriting the laws of physics as it swept across existence. The familiar bonds that tie atoms together might no longer hold. Forces that govern matter and energy could shift or vanish altogether. There would be no warning, no anticipation, only the sudden redefinition of reality itself as the bubble grew until it encompassed the observable universe. To imagine such a fate is to confront the ultimate fragility of existence, though from the human perspective it would arrive instantaneously, leaving no time for fear or response. Yet even in its starkness, the notion of vacuum decay highlights the extraordinary complexity of the physical laws that allow the universe to exist at all. In contrast to these dramatic scenarios stands the historical idea of the steady-state theory. This model proposed a cosmos without beginning or end, a universe in perpetual balance where new matter continually appeared to maintain constant density as galaxies drifted apart. For some, it suggested a world stripped of overarching purpose, a timeless system with no direction beyond endless continuity. For others, it offered the liberating vision of an eternal cosmos in which renewal was unceasing and possibilities were infinite. But the discovery of the cosmic microwave background radiation revealed unmistakable evidence of a hot, dense origin, lending powerful support to the Big Bang model and leaving the steady-state theory in disrepute. The transition from a static eternal vision to one of origin, growth, and expansion fundamentally reshaped how humanity perceives its cosmic story. No longer a realm without beginning, the universe became a process with a trajectory, inviting contemplation of cycles, endings, and perhaps renewal on scales beyond comprehension. The expansion rate of the universe itself became a central key to unlocking its destiny. Measured by the Hubble constant, this rate defines how quickly galaxies are receding from one another. If the pull of gravity someday outweighed this expansion, the universe might slow, halt, and reverse in a great collapse, culminating in a big crunch where all matter returned to an incomprehensibly dense point. If expansion proved stronger, the cosmos could grow colder and emptier, fading into the big freeze as stars exhausted their fuel and galaxies receded into darkness. Or expansion could accelerate so violently that it shattered every structure in existence, a big rip tearing apart galaxies, stars, planets, and even the atomic fabric of matter. Observations suggest acceleration is indeed the course of our universe, propelled by the enigmatic influence of dark energy. Yet this force, so fundamental to the fate of everything, remains shrouded in mystery, its essence unknown, its implications immense. Across all these possibilities runs a deeper theme. The universe is not static, but an evolving entity undergoing transformations akin to phase changes in ordinary matter. Just as ice becomes water and water becomes vapor, the universe itself has shifted through epochs defined by changing conditions. In the earliest fractions of a second after the Big Bang, as temperatures dropped, the fundamental particles of matter were forged. Quarks bound together to form protons and neutrons, laying the groundwork for the eventual rise of atoms, stars, galaxies, and life itself. Each transition unlocked new potential, new structures, new complexity. These cosmic transformations reveal a universe not only vast but profoundly dynamic, a reality in motion where even the constants of existence may not be constant forever. To witness, even in imagination, such a grand unfolding is to recognize both the tenuousness and the magnificence of our place in this evolving cosmos. Looking forward, physicists speculate about potential future phase transitions that could dramatically alter the universe's landscape, and they speak of these possibilities with a mixture of sober calculation and story-like imagination. In lecture halls, at kitchen tables, and in the quiet of night observatories, researchers map out scenarios that read like cosmic thought experiments. The slow, almost polite rearrangement of the vacuum itself, a sudden flip in the invisible pressure that now drives space to speed apart, the long, patient fading of stars until only the hard skeletons of stellar death remain. Each scenario is a different possible ending to the same account, and each reveals how fragile the framework of existence can be when probed by the cold logic of physics. One particularly unsettling possibility is vacuum decay. Our present universe, the one we measure with telescopes and particle colliders and the rhythm of atomic clocks, may be parked in what physicists call a false vacuum, a temporary valley in the landscape of possible energy states. It is a place of relative calm that is not, in the deepest sense, the true ground state. In the language of the theory, the field that sets particle masses and interaction strengths might be sitting in a shallow trough. If a quantum fluctuation or a catalyzing event nudged the field over a barrier, a bubble of true vacuum could form. That bubble would expand at close to the speed of light, and the rules inside it could be entirely different. Fundamental constants might take new values. Particles might no longer hold together the way they do. Chemistry, the architecture of stars, the scaffolding of galaxies could be rewritten in the span of a heartbeat as measured by distant observers. To us, inside the false vacuum, the event would be sudden, absolute, and beyond any hope of mitigation. The haunting logic of vacuum decay is not that it is likely in any human timescale, but that it is permitted by the mathematics of quantum field theory and by certain measurements of particle behavior. It turns cosmology into a drama with an unpredictable curtain. The thought of a latent instability in the bedrock of physics forces a reassessment of what stability really means. What we call laws of nature might be conditional, contingent on the particular energy basin in which our universe happens to sit. The notion does not merely threaten habitability, it would undercut the very continuity of cause and effect that makes science possible. Another set of possible transitions involves dark energy, the invisible influence discovered toward the end of the 20th century that accelerates the cosmic expansion. Dark energy is a name for phenomenon, not a single theory, and that linguistic caution hides a wide landscape of theoretical options. Some ideas treat dark energy as a constant property of space, an unchanging cosmological constant that simply adds a uniform pressure to the fabric of the universe. Other ideas imagine a dynamic field, one that can evolve and shift. If dark energy were to change its character, the expansion history of the cosmos could be transformed. Consider a future where dark energy grows in strength. Structures bound by gravity could be pulled apart in a scenario popularly known as the Big Rip. Galaxies would drift beyond each other's horizons, then star systems would unbind, then planets would leave the orbits that once held them, and finally even atoms could be torn asunder as expansion overwhelmed the forces that bind matter. At the opposite extreme lies the possibility of a reversal. If dark energy were to weaken or reverse sign, expansion could slow, halt, and then invert into contraction. The universe might curve back toward a dense state in a cosmic contraction, sometimes called a big crunch. Between these dramatic endpoints, there are subtler possibilities: phases of punctuated acceleration, epochs of relative calm, or slow drifts that would change galactic dynamics over time so long that they challenge human intuition. Exploring these options is not idle speculation, but the work of careful observation and mathematical modeling. Astronomers measure the brightness of ancient supernovae, map the subtle distortions of background radiation, and count the clustering of galaxies across cosmic time. Each data point tightens the constraints on how dark energy can behave, and thus refines the set of allowed futures. The science is incremental and cumulative, yet the scenarios it allows retain an almost mythic quality because they speak to the ultimate fate of everything. If the universe's large-scale evolution sets the stage, the microcosms of stellar death provide a catalog of final acts that are at once practical and profound. White dwarfs and neutron stars are not merely curiosities. They are the long-lived embers of stellar life and living laboratories for extreme physics. White dwarfs begin their existence as ordinary stars like our sun, but after exhausting the thermonuclear fuel that sustains fusion, they shed their outer layers and leave behind a compact core. This remnant is about the size of Earth while carrying mass comparable to the sun, and it resists collapse not by fusion, but by the quantum pressure of electrons. That pressure is a direct consequence of the rules of quantum mechanics, and the behavior of white dwarfs becomes a measurable testament to the interplay between quantum principles and astrophysical conditions. As white dwarfs cool over immense spans of time, they become cosmic clocks. By studying populations of these cooling embers, astronomers calibrate the age of stellar populations and obtain independent estimates for the age of the universe itself. Observations of the faintest, oldest white dwarfs inform projections about the far future when, in most plausible scenarios, the cosmos will be a darker, quieter place. In those distant epochs, white dwarfs will be among the last luminous beacons, slowly radiating away residual heat until they fade into inert black dwarfs, cold and inert. Neutron stars are a different sort of relic, born from the gravitational collapse of stars much more massive than the Sun. When such a star explodes in a supernova, its core can be compressed beyond the scale at which electrons and protons remain distinct, yielding a compact object whose interior is a dense sea of neutrons. These stars pack solar mass into a sphere roughly a dozen kilometers across. Their densities strain our theories, forcing physicists to confront matter under pressures and densities impossible to reproduce on Earth. Observations of neutron star masses, radii, and their violent collisions probe the nuclear equation of state, reveal the behavior of superfluids and superconductors under extreme conditions, and help refine models of how matter organizes itself when the ordinary order is stripped away. Together, white dwarfs and neutron stars form a bridge between the astronomical and the subatomic. Their existence confirms broad aspects of stellar evolution and, by extension, the reliability of the physical laws that govern that evolution. At the same time, measurements of their behavior across vast distances contribute to cosmology. They serve as both probes of local physics and as markers in the cosmic expansion, helping researchers infer how space itself has stretched and how it may continue to do so. The picture that emerges from decades of observation and theory is one of plausible continuity. The universe may continue to expand and cool, stars will finish their lives and leave behind cold remnants, and the large-scale structures will move ever farther apart. In such a heat-death scenario, the cosmos becomes cold and dark, a vast expanse populated by silent stellar corpses and diffuse clouds of rarefied particles. Yet even as this shadowy future seems bleak, it is fertile with questions. How long will quantum processes persist? What remains of information encoded in those final objects? And how do we define existence when the lights go out across cosmic scales? Intertwined with these physical forecasts is a philosophical current that moves from empirical science into the realm of metaphysical possibility. The concept of a simulated universe reorients the whole conversation. Rather than asking what will happen if the laws of physics change, it asks whether what we call laws might be the output of computational rules in a higher level system. Under the simulation hypothesis, our universe would be an enacted model, a vast program designed and executed by entities with technological capabilities far beyond our own. Within such a frame, the constants, symmetries, and apparent regularities of nature would be artifacts of code, rather than absolute truths. If a simulation were at play, it raises an array of consequential questions. Was the simulation intended as experiment, entertainment, education, or something else we cannot imagine? Would the creators have a motive that maps onto observable features of the universe? Could anomalies or patterns we struggle to explain be evidence of design choices or computational limitations? The hypothesis also reframes debates about free will, consciousness, and meaning. If minds are emergent within a computational substrate, then in principle the mechanisms of cognition could be instantiated, duplicated, or modified. The possibility opens speculative doors toward forms of extended existence in which consciousness is preserved or transferred, at least within the vocabulary of computational metaphors. At the same time, the simulation idea does not strip human experience of significance. Even if our world were a modeled environment, the interior reality of sentient beings within it would remain subjectively real. Beauty, discovery, suffering, and joy would still be phenomena that matter to those who live through them. The discourse then shifts. Purpose is not an absolute cosmic property, but potentially a relational feature, defined by the creator's aims or by the meanings that simulated agents themselves construct. The hypothesis thus invites a new kind of humility and curiosity, urging a recognition that our explanatory frameworks might be nested inside deeper structures we cannot yet access. Across all these narratives, vacuum decay, dark energy transitions, the longevity of stellar remnants, and the simulation hypothesis, one theme recurs. The cosmos resists complacency. Its possibilities include slow, inexorable fades and sudden, universe-sweeping changes. The same equations that allow for precision predictions also admit dramatic uncertainties. In the laboratories where detectors hum and on the telescopes that scan the night, scientists gather evidence and refine models not because they desire cosmic dread, but because understanding the range of possible futures sharpens the present. The work is an act of translation, turning abstract mathematical potential into concrete scenarios that can be tested and, where possible, constrained. The study of the universe's future is therefore an exercise in imagination, anchored by method. It is documentary in spirit, a careful record of what could be next, told in the language of observation, experiment, and theory. It keeps open the prospect that the present is provisional, that the constants we take for granted are chapters in a larger tale, and that the universe, whether natural or designed, is a theater of processes that will continue to surprise those who keep watching. Furthermore, this hypothesis compels us to fundamentally reconsider our place in the vast, intricate cosmos that stretches beyond our perception. If we are indeed simulated beings, our existence may be nothing more than a segment of a grand experiment, a sophisticated form of entertainment for civilizations far beyond our comprehension, or an extraordinarily complex computational model designed to solve problems of immense scale and subtlety. This perspective dramatically reshapes our understanding of purpose, value, and meaning in the universe, forcing us to interrogate beliefs and assumptions that once seemed unassailable. The very notion that our lives, decisions, and experiences might be components of a deliberately designed simulation challenges our deepest intuitions about free will, individuality, and the significance of conscious thought. Nested simulations and the concept of multiple universes push the boundaries of imagination even further, destabilizing conventional ideas of reality and cosmic intention. The concept of nested simulations proposes that our universe might be a single computational layer embedded within a larger, more complex universe, which itself could exist inside yet another simulation, potentially leading to an infinite hierarchy of realities stacked within one another. This intricate layering introduces a mind-bending hierarchy, suggesting that each reality could be a derivative or projection of a higher-order universe, a structure that challenges even the most sophisticated philosophical frameworks for understanding existence. Parallel to this, the idea of multiple universes, often referred to as the multiverse theory, posits that entirely separate, self-contained realities could exist, each governed by its own physical laws, constants, and forms of life. While the multiverse implies plurality and diversity of independent worlds, nested simulations introduce hierarchy and intentionality, suggesting a chain of creation and observation that may extend indefinitely. Both concepts radically expand our understanding of what might lie beyond the observable universe, prompting questions about whether our own universe is a unique endpoint or merely one layer within an endlessly intricate system. The implications for cosmic purpose in this context are profound and unsettling. If we inhabit a simulation, the intentions of the simulators become paramount. Are we the subjects of a meticulous experiment, an elaborate form of amusement, or participants in a computational exploration designed to test outcomes and scenarios beyond their own universe? Conversely, the existence of multiple universes raises the possibility that our cosmos is one among countless outcomes, each possessing unique properties, laws of physics, and potentially entirely new forms of life and consciousness. Such ideas challenge traditional anthropocentric notions of cosmic purpose, suggesting instead that our universe might be a single node within a vast, interconnected web of realities, where meaning and significance transcend the boundaries of what we perceive as real. They invite us to envision a broader existential framework in which human understanding is only the beginning of a journey toward comprehending the true architecture of existence. The role of computational power is central to the feasibility of simulating entire universes. As humanity's technological capabilities grow and our understanding of cosmic processes deepens, the question of whether an entire universe could be digitally modeled becomes increasingly tangible. The scale and complexity of the cosmos, however, present extraordinary challenges. Accurately simulating even a fraction of the universe demands the ability to track and calculate every particle, every interaction, and every fundamental force in real time. Current supercomputers, despite their immense power, remain woefully insufficient for such an endeavor. Yet, advances in quantum computing offer a glimmer of possibility. Quantum systems, capable of performing complex calculations exponentially faster than classical machines, might one day enable the simulation of smaller, simplified universes, providing unprecedented insights into cosmic evolution and the underlying principles of reality. Even so, the enormity of a universe simulation, encompassing every atom and energy exchange, remains a daunting frontier, suggesting that the full realization of such a project lies far in the future. Digital physics introduces a provocative framework for understanding this potential. It proposes that the universe, at its most fundamental level, operates like a colossal computational system, processing information through discrete units rather than continuous flows. In this view, space and time are quantized, resembling pixels on a screen or bits in a computer, mirroring the discretized structure found in advanced simulations. If our universe adheres to principles of digital physics, it provides circumstantial support for the simulation hypothesis, implying that the cosmos itself could be algorithmic in nature, with complex processes emerging from simple computational rules. The simulated cosmos hypothesis further suggests that an advanced civilization could, in theory, construct a universe so detailed that its inhabitants remain entirely unaware of its artificial origins. While these ideas remain speculative, ongoing scientific inquiry continues to probe the fabric of reality, searching for evidence that might confirm or refute the notion that our universe is, in essence, a sophisticated digital construct. The ethical ramifications of creating simulated universes are equally profound. If future technology enables the creation of artificial realities populated by conscious entities, humanity would face unprecedented moral dilemmas. Simulated beings capable of suffering or experiencing joy could demand ethical consideration equivalent to that extended to sentient life on Earth. Additionally, questions arise regarding the degree of intervention appropriate within such simulations. Should creators actively influence events or allow the emergent processes to unfold autonomously? These considerations echo timeless philosophical debates about free will and determinism, now projected onto the canvas of artificial realities. Finally, the potential that our own universe is a simulation poses deeply unsettling existential questions. If we can conceive of creating such detailed artificial realities, it is conceivable that a civilization far beyond our own has already done so. Acceptance of the simulation hypothesis would force a radical rethinking of cosmic purpose. Our universe, with all its galaxies, physical laws, and sentient life, might be a deliberate construct, designed to achieve objectives set by an intelligence whose motives are inscrutable to us. Are we an experiment, entertainment, or a preservation mechanism for knowledge long lost to a higher civilization? This possibility transforms our understanding of the cosmos from a naturally evolving entity into a system with intentional design, suggesting that the ultimate meaning of our existence could lie in the intentions of those who created it, forever intertwining our reality with a greater, unseen architecture of purpose. Furthermore, the discovery of a simulated universe would profoundly transform our understanding of consciousness, free will, and the very foundations of existence. If we were to find evidence that our reality is not the ultimate physical world, but a constructed computational framework, it would imply that our thoughts, decisions, and actions may be programmed, integral parts of a vast, intricate system of algorithms rather than products of independent agency. This revelation would force us to reconsider the meaning and purpose we ascribe to life, both on an individual level and across the cosmic scale. Detecting such a simulation would not render the search for significance futile. Instead, it would deepen and complicate our inquiry, introducing entirely new dimensions to our exploration of reality, consciousness, and the origins of purpose itself. Consciousness, in this context, assumes an extraordinary and enigmatic role. As we contemplate artificial worlds, we must probe the ways in which our awareness and perception might function within these synthetic constructs. Within a simulated reality, consciousness could serve as the vital interface connecting subjective experience to the rules and structures of the artificial environment. Much as our minds allow us to navigate the physical world, consciousness in a simulation might provide the capacity to interpret, respond to, and manipulate a constructed universe. Yet, this notion raises fundamental questions about the authenticity of our experiences. If our perception of the universe is mediated by a programmed framework, what does this say about the reality of those experiences or the essence of the reality itself? One tantalizing hypothesis is that consciousness could emerge as a property of sufficiently complex simulations. This suggests that as artificial environments grow in sophistication, they might spontaneously generate self-aware entities, blurring the line between synthetic and genuine consciousness. Such a possibility challenges our conventional understanding of self-awareness, implying that intelligence and subjective experience might not be exclusive to the so-called real world, but could arise naturally within artificial systems. This perspective also prompts us to confront the unsettling idea that our own universe could be a simulation. If we possess the capability to construct convincing artificial realities, then by extension, how can we be certain that our own conscious experience is not the product of a far more advanced civilization or even a future iteration of ourselves? The simulation hypothesis, as this notion is known, forces a radical reevaluation of consciousness, placing it at the heart of our understanding of existence. Emergent phenomena become particularly significant in the context of simulated universes. These phenomena arise when simple, interacting components give rise to complex behaviors or structures that cannot be predicted solely from the properties of the individual parts. Within a simulated universe, this principle suggests that even if the foundational rules are straightforward, intricate and unpredictable patterns, ranging from physical structures to life and intelligence, can spontaneously develop. Consider cellular automata. Simple mathematical rules governing grids of cells can produce astonishingly elaborate, almost lifelike patterns. Similarly, a universe governed by elementary laws might naturally generate emergent phenomena, including self-organizing systems, consciousness, and perhaps even forms of intelligence. The implications of emergence extend to our understanding of cosmic purpose. If a simulated universe can produce unexpected complexity from simple rules, then purpose itself may be an emergent property, not a predetermined directive imposed by an external creator. In this view, the universe's meaning is not explicitly written into the fabric of reality, but evolves naturally from the interactions of its constituent elements. This perspective encourages a radical rethinking of cosmology and philosophy, suggesting that intelligence, complexity, and purpose may arise spontaneously from fundamental principles in ways that challenge our current comprehension of existence. The simulation hypothesis also provokes deep reflections on free will and determinism. If reality is computationally generated, every thought, action, and event could theoretically result from pre-programmed algorithms, aligning with a deterministic view, where all occurrences are the inevitable consequence of prior conditions. In such a scenario, the concept of free will seems precarious. Our decisions might be complex computations rather than autonomous acts. Yet, even within a simulated framework, free will need not vanish entirely. The sophistication of consciousness may permit genuine choice within the constraints of the system, analogous to a player navigating a richly detailed video game environment. Decisions are made, interactions occur, and consequences unfold, but always within a defined set of parameters. Moreover, the simulation hypothesis introduces the possibility of nested realities, where the beings running a simulation could themselves inhabit a higher-level simulation. This recursive structure complicates the nature of causality and agency, making it increasingly difficult to discern the origin of actions or the scope of true autonomy. Our understanding of free will, therefore, must account for the potential multiplicity of simulated layers, where choices may exist, but always within boundaries set by higher-level rules. In essence, the discovery of a simulated universe and the exploration of consciousness and emergence within it would revolutionize philosophy, science, and our sense of self. It challenges long-held assumptions about reality, agency, and purpose, compelling us to consider that intelligence, consciousness, and meaning may not be external gifts imposed upon a passive universe, but emergent features woven into the very structure of existence itself, whether simulated or real.